Time is by far one of the most fundamental levels of physics. It is the measure of change, the invisible framework that allows us to track the universe, compare events, and define the sequence of cause and effect. Unlike physical objects, time has no shape, weight, or form. It exists as a continuous progression, flowing forward without pause. At its core, time provides structure to the universe. A second is defined by the vibrations of atoms, a day by the Earth's rotation, and a year by its orbit around the Sun. These natural cycles give time a tangible presence, allowing us to measure and organize reality. Without time, events would have no order and motion would have no meaning. But time is more than just a measurement. It is a fundamental dimension of existence. It governs how processes unfold, from the movement of celestial bodies to the rhythms of biological life. Plants grow, tides shift, and seasons change, all following the passage of time. Position. This is the fundamental reference point of motion. Every object exists somewhere in space, and describing its position is the first step in understanding movement. But position is not absolute. It is always measured relative to something else. In physics, position is defined using a coordinate system. A simple number line can describe motion in one dimension, where moving forward increases position values and moving backward decreases them. In 2 dimensions, coordinates on a map pinpoint exact locations. In 3 dimensions, objects move through space with x, y, and z coordinates, defining their position at any given moment. But position is not just about location, it depends on the observer. A train moving past a station appears in different positions depending on whether you're inside the train or standing on the platform. This idea, known as the frame of reference, is crucial in physics. The same object can have different positions depending on the point of view, which influences how we measure motion. Position also plays a key role in navigation and measurement. Whether tracking a satellite in orbit, locating an earthquake's epicenter, or mapping the movement of tectonic plates, understanding position allows us to describe and predict how objects move through space. Distance. It is one of the most necessary concepts in physics, describing how far an object has traveled from one point to another. Unlike position, which specifies a location, distance is purely a measure of length. It accounts for the total path covered, regardless of direction. Imagine a car moving along a winding road. If it starts at one point, follows a curved route, and arrives somewhere else, the distance traveled is the sum of all the segments of its journey. Even if the car returns to its starting point, the total distance remains the entire length of the trip. Distance is a scalar quantity, meaning it has only magnitude, not direction. This distinguishes it from displacement, which measures the shortest straight-line path between 2 points. For example, a person walking around a city block may travel a long distance, but their displacement is just the direct separation between their starting and ending points. In everyday life, distance is measured using units like meters, kilometers, or miles. It helps us navigate roads, measure heights, and calculate depths. In science, precise distance measurements are essential for mapping microscopic structures, analyzing planetary motion, and even understanding the scale of the universe. From the smallest atomic interactions to the vast distances between galaxies, the concept of distance allows us to quantify movement and size. Whether measuring the span of a room or the reach of a star, distance serves as a foundation for understanding physical space and motion. Mass. One of the most fundamental levels of physics, it defines the presence of matter, giving everything from the tiniest particles to the largest galaxies a measurable existence. Without mass, objects wouldn't have substance, weight, or resistance to motion, fundamental traits that shape the physical world. At its core, mass quantifies how much matter an object contains. It remains constant regardless of location or external forces. A bowling ball is harder to lift than a tennis ball because it contains more mass. Unlike weight, which depends on gravity, mass is an inherent property of an object that does not change whether it's on Earth, the Moon, or floating in deep space. Mass also determines how objects interact through gravitational attraction, the reason planets stay in orbit, why things fall when dropped, and why stars cluster together is due to mass. More massive objects exert stronger gravitational forces, influencing everything from planetary motion to the structure of the universe. In everyday life, mass is measured using balances or scales, which compare an object's resistance to gravitational pull. In space, where gravity is absent, mass is determined by how much force is needed to accelerate an object. These measurements are crucial in physics, engineering, and even daily activities like cooking or construction. Mass is not just a number. It is the foundation of all physical interactions. It dictates how objects respond to forces, how they interact with gravity, and how the universe itself is structured. Understanding mass is the first step in unraveling the fundamental principles that govern the physical world. Motion is the foundation of change in the universe. From the drifting of galaxies to the shifting of a grain of sand, nothing remains truly still. Even in the most motionless state, atoms vibrate, planets rotate, and space itself expands. Motion is not just movement. It is the defining characteristic of existence. At its simplest, motion is the change in position of an object over time, relative to a chosen reference point. A car passing a stationary observer on the sidewalk is in motion, yet to a passenger inside it appears still. The movement of an object can only be described when compared to something else. Motion is always relative. Every type of motion follows specific patterns. Some motion is uniform, where an object moves at a constant rate in a straight path. Other motion is non-uniform, where speed or direction changes over time. The swing of a pendulum, the orbit of the moon, or the rise and fall of ocean tides are all forms of motion shaped by forces acting upon them. Motion can be linear, like a falling rock, or circular, like a spinning wheel. It can be periodic, like the back and forth swing of a clock's pendulum, or chaotic, like the erratic movement of molecules in a gas. No matter the form, motion governs how objects interact, how energy transfers, and how systems evolve over time. Understanding motion is essential to understanding the physical world. It dictates the patterns of nature, from the simplest falling leaf to the vast movements of celestial bodies. Recognizing and analyzing motion is the first step in exploring the deeper principles that define the mechanics of the universe. Speed. This measures how quickly something moves from one place to another. It is the rate at which distance is covered over time, making it one of the most fundamental aspects of motion. Whether it's a car traveling down a road, a person running, or sound moving through the air, speed describes how fast an object is in motion. At its core, speed is simply the total distance traveled divided by the time taken. If a train covers 200 kilometers in 4 hours, its average speed is 50 kilometers per hour. Since speed only tells us how fast something moves, not in which direction, it is classified as a scalar quantity. Speed is everywhere in daily life. Walking casually, a person moves at about 5 kilometers per hour. A plane cruises through the sky at nearly 900 kilometers per hour. The fastest land animal, the cheetah, can reach speeds of over 100 kilometers per hour. But even these are slow compared to astronomical speeds. The Earth orbits the Sun at about 107,000 kilometers per hour, and light itself travels at nearly 300,000 kilometers per second. Understanding speed allows us to measure, compare, and predict movement in everything from transportation to natural phenomena. It helps engineers design faster vehicles, scientists study motion in physics, and astronomers calculate distances across space. Whether it's measuring the pace of daily activities or tracking objects moving at cosmic scales, speed is an essential concept that defines how things move through the world. Velocity. Velocity is more than just speed. It's speed with direction. While speed measures how fast something moves, velocity specifies both how fast and in which direction. This distinction makes velocity a vector quantity, meaning it has both magnitude and direction. Imagine a car moving at 60 kilometers an hour. If it's traveling east, its velocity is 60 kilometers per hour east. If it turns west at the same speed, the velocity changes, not because the speed changed, but because the direction did. This makes velocity a more complete description of motion than speed alone. In everyday life, velocity helps describe motion more accurately. A plane flying at 800 kilometers per hour is not just moving. It has a velocity based on its direction. The wind's velocity determines whether a flight is delayed or arrives early. Ocean currents influence ships based on their velocity. Even in sports, understanding velocity is key, whether it's tracking the path of a baseball or calculating the trajectory of a soccer ball. In physics, velocity is essential for describing motion across all scales. It defines how objects move, how trajectories are calculated, and how motion is predicted. Whether it's tracking planetary orbits, measuring fluid flow, or studying moving particles, velocity allows precise analysis of movement. By knowing both speed and direction, velocity provides a complete picture of how objects travel through space. It forms the foundation for understanding motion in mechanics, navigation, and even astrophysics, making it one of the most fundamental concepts in physics. Acceleration. It describes how motion changes. Whether a car speeds up, slows down, or turns a corner, it is experiencing acceleration. Unlike speed, which measures how fast something moves, or velocity, which adds direction, acceleration measures how quickly velocity changes. At its core, acceleration is the rate of change of velocity over time. If a car is moving at 20 mph and increases to 30 mph in 5 seconds, it has an acceleration of 2 ms2. But acceleration isn't just about speeding up. It also includes slowing down, known as deceleration, and changing direction. A car turning at a constant speed is still accelerating because its velocity is changing. Acceleration is a key concept in describing how objects move, from everyday activities to astronomical phenomena. When you push off on a bicycle, the increase in speed is acceleration. The jolt you feel in an elevator when it starts or stops is acceleration. Even Earth itself accelerates as it follows its curved orbit around the Sun. Gravity is one of the most familiar sources of acceleration. Any object falling freely near Earth's surface accelerates at 9.8 ms2, regardless of its mass. This explains why two objects dropped from the same height fall at the same rate, assuming air resistance is negligible. Whether tracking a moving vehicle, studying falling objects, or analyzing planetary motion, acceleration provides a fundamental way to describe and predict changes in movement. Understanding acceleration allows us to analyze motion with precision, making it an essential concept in physics. Force. Nothing moves, stops, or changes without force. It's the invisible hand behind every motion, from a falling raindrop to the movement of massive tectonic plates. Without force, the world would be static. No flowing rivers, no shifting clouds, no movement of objects. At its core, force is simply an interaction that causes a change in motion. It can make something start moving, stop, or change direction. A force applied to an object can speed it up or slow it down. The more force exerted, the greater the effect. Pushing an empty cart is easy, but a loaded one requires more effort. This is because greater mass requires a greater force to achieve the same motion. Forces come in many forms. Contact forces require physical interaction like friction and applied force. Try sliding a book across a table. Friction resists the motion, slowing it down. Push a door, and it moves in response to the applied force. Forces can also be balanced or unbalanced. When equal forces act in opposite directions, there is no movement, like two people pushing against each other with equal strength. But when forces are unbalanced, motion occurs. The stronger force overcomes the weaker, setting objects into motion or altering their speed. From the pull of a stretched rubber band to the impact of a hammer striking a nail, every action is governed by force. Whether subtle or immense, force is the reason objects move, interact, and respond to their surroundings, making it one of the most fundamental principles in physics. Inertia. This plays a crucial role in shaping everything from daily experiences to large-scale cosmic interactions. It's the reason why a bicycle stays upright when moving, but topples when stationary. why astronauts in space continue floating without resistance, and why heavier objects require more effort to move or stop. Inertia isn't just a property of objects, it's a fundamental characteristic of matter itself. Engineers and scientists rely on inertia to design safer vehicles, stable bridges, and efficient machinery. Crumple zones in cars are built to counteract inertia during a crash, absorbing impact forces to reduce harm. In sports, understanding inertia helps athletes control motion, whether it's a runner maintaining momentum or a gymnast sticking the landing. Even in space exploration, spacecraft must account for inertia, using precise thrusts to adjust course since objects in a vacuum will continue moving indefinitely without external resistance. On a grander scale, inertia governs planetary motion. The Earth orbits the Sun not because it is actively propelled, but because inertia keeps it moving while gravity bends its path into an orbit. The same principle applies to galaxies, where vast celestial bodies move in predictable patterns due to their own inertia. Recognizing inertia allows us to predict movement, control forces effectively, and innovate in fields ranging from transportation to astrophysics. Whether it's the stability of buildings, the efficiency of machines, or the mechanics of motion, inertia is a silent but ever-present force shaping the physical world. Momentum. It is the reason a moving train takes miles to stop, why a bullet can pierce steel, and why catching a fast-moving ball stings your hand. It's not just motion, it's motion with impact. Momentum is the product of an object's mass and velocity. The greater the mass or speed, the more momentum it carries. This is why a slow-moving truck can have more momentum than a speeding bicycle. It's all about mass and motion combined. Momentum is also a vector quantity, meaning it has both magnitude and direction. A car moving east at 60 miles per hour has momentum in that direction. Change its speed or direction, and its momentum changes as well. One of the most fundamental principles in physics is the conservation of momentum. In a closed system, momentum is never lost. It only transfers. This is why in collisions, the total momentum before impact equals the total momentum after. In elastic collisions, like two billiard balls striking, momentum transfers with minimal energy loss. In inelastic collisions, like a car crash, some momentum converts into sound, heat, or deformation. Momentum also plays a role in space travel. Since there's no air resistance in space, astronauts rely on conservation of momentum to maneuver. Push an object in one direction, and you'll move in the opposite. Momentum governs how objects interact, transfer energy, and continue moving until something stops them. Impulse. A boxer takes a punch. A baseball bat strikes a ball. A car airbag inflates in milliseconds. Each of these moments is governed by impulse, the force that changes an object's momentum. Impulse is the product of force and the time over which it acts. When a force is applied to an object, it changes its momentum. The longer the force is applied, the greater the change. This relationship is captured by the equation, impulse force time. Imagine kicking a soccer ball. A quick tap sends it rolling slowly, but a strong, sustained kick launches it across the field. The difference? More impulse. A greater force over a longer time transfers more momentum. Impulse also explains how safety mechanisms work. A car crash can be deadly, but airbags and crumple zones extend the time over which the collision occurs, reducing the force experienced by passengers. Instead of an abrupt stop, the gradual deceleration spreads the impulse over time, reducing injury. In sports, impulse determines performance. A golfer follows through on their swing to keep contact with the ball longer, maximizing impulse and distance. A baseball player catches a fast-moving ball by pulling their glove back upon impact, extending the time and reducing the force on their hand. Impulse is everywhere, from shock absorbers in cars to how we land after a jump. Impulse shapes movement, impact, and safety. It's the hidden factor behind every collision, every acceleration, and every split-second reaction that alters momentum in the real world. Newton's laws. These are the foundation of classical physics, governing how objects move and interact with forces. These three simple yet profound principles explain everything from the flight of rockets to the way you push a door open. The first law, often called the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. Imagine a book lying on a table. It won't move unless you push it. Likewise, a moving car doesn't stop instantly when the brakes are applied. It resists the change in motion, a result of inertia. The second law defines the relationship between force, mass, and acceleration. Force-mass acceleration. This means the harder you push an object, the faster it accelerates. A heavier object, however, requires more force to achieve the same acceleration. That's why kicking a soccer ball sends it flying, but kicking a bowling ball hardly moves it. This law is the key to understanding how everything from bicycles to spacecraft operate. The third law is often summarized as, for every action, there is an equal and opposite reaction. When you jump off a boat, you push the boat backward while propelling yourself forward. Rockets work the same way. By expelling exhaust gases downward, they generate thrust upward. These three laws together explain motion in nearly every situation imaginable. Whether predicting planetary orbits or engineering high-speed trains, Newton's principles remain indispensable. They are the building blocks of physics, providing a framework for understanding forces, movement, and interaction in the physical world. Gravity. This is the silent architect of the universe. It keeps planets in orbit, shapes galaxies, and holds everything together, including you right now, pressing against the ground. Without gravity, there would be no Earth as we know it. No atmosphere, no oceans, no stars. It is the force that governs structure and motion on every scale. At its most fundamental level, gravity is the attraction between any two objects with mass. The greater the mass, the stronger the pull. This is why Earth's gravity keeps the moon in orbit, while the sun's immense gravity holds the planets in place. Newton's law of universal gravitation states that every mass exerts a force on every other mass, and this force weakens with distance. But Newton's explanation was only part of the story. Einstein's theory of general relativity redefined gravity as the bending of space-time. Imagine placing a heavy ball on a stretched rubber sheet. The surface curves around it. A smaller ball placed nearby will roll toward the dent, just as a planet orbits a star following the curved path created by its mass. This is why gravity isn't just a force, it's the shape of reality itself. Gravity isn't just about holding things down. It determines how time flows. Stronger gravitational fields, like those near black holes, slow time relative to weaker ones. This effect, known as gravitational time dilation, has been confirmed by atomic clocks on satellites, which tick slightly faster than those on Earth's surface. Every movement in the universe, from falling objects to the expansion of the cosmos, is shaped by gravity. It is both familiar and mysterious, pulling everything toward everything else in an endless cosmic dance. Free fall. Free fall is motion in its purest form, an object moving under the influence of gravity alone, without resistance, without interference. Whether it's a skydiver leaping from a plane or an apple dropping from a tree, free fall is nature's simplest demonstration of gravity in action. In a vacuum, where air resistance is removed, all objects, regardless of mass, fall at the same rate. This was famously demonstrated by Galileo at the Leaning Tower of Pisa, and later confirmed on the moon when an astronaut dropped a feather and a hammer, both hitting the surface simultaneously. The acceleration due to gravity on Earth is approximately 9.8 ms2, meaning that every second a freely falling object increases its speed by 9.8 m/s. Free fall isn't just about objects dropping to the ground. It extends to celestial mechanics. The moon is technically in perpetual free fall around Earth. Its motion is curved into an orbit rather than a straight descent. Satellites, too, are constantly falling toward Earth, but their forward velocity keeps them in orbit instead of crashing down. Even when you experience weightlessness, such as in space or during the zero-gravity flight, you're still in free fall, just falling at the same rate as your surroundings. This is why astronauts appear to float. They aren't defying gravity. They are simply in a state where gravity is the only acting force. Free fall reveals the fundamental nature of gravitational motion: universal, inevitable, and independent of an object's properties. Whether an object is as light as a feather or as heavy as a rock, if gravity is the only force acting, the rules remain the same. Friction. Friction is the invisible force that slows motion, wears down surfaces, and keeps objects from sliding endlessly. Without it, walking would be impossible, cars wouldn't stop, and nails wouldn't hold wood together. It is both an obstacle to movement and a necessity for control. At its core, friction arises when two surfaces come into contact, resisting their motion relative to each other. Even the smoothest materials have microscopic irregularities, and when pressed together, these tiny bumps interlock, creating resistance. The rougher the surface, the greater the friction. There are two main types: static friction and kinetic friction. Static friction keeps objects at rest. Imagine trying to push a heavy box. At first, it doesn't move because static friction resists your effort. Once you push hard enough, the box starts sliding, transitioning into kinetic friction, which is weaker but still slows motion. This is why it takes more effort to start moving an object than to keep it moving. Friction also depends on normal force, the force pressing two surfaces together. This is why a heavier object pressing down harder experiences more friction. However, friction doesn't depend on surface area. A wide tire and a narrow tire on the same road experience roughly the same friction because force distribution, not contact area, is the key factor. Friction is everywhere. It enables brakes to stop vehicles, allows athletes to grip surfaces, and even generates heat when you rub your hands together. Engineers work to reduce friction in machines using lubricants, while athletes and drivers find ways to increase it for better control. Whether slowing motion or enabling it, friction governs how objects interact with their surroundings, making it one of the most fundamental forces in everyday life: air resistance. Not all falling objects obey the simple rules of free fall. Drop a rock and a feather, and the rock reaches the ground first. Not because it's heavier, but because of air resistance, the force that opposes motion through air. This invisible force can slow objects, shape flight paths, and even allow humans to glide through the sky. Air resistance, or drag, occurs because air is made of molecules. As an object moves, it must push these molecules aside. The faster it moves, the more collisions occur, increasing resistance. This is why cyclists hunch forward to reduce drag, and why parachutes expand to maximize it. The effect of air resistance depends on speed, shape, and surface area. A streamlined object like a bullet cuts through air with minimal resistance, while a broad parachute creates significant drag, slowing descent. This force is why skydivers plummet quickly at first, but then stabilize at terminal velocity, the point where gravity and air resistance balance out, preventing further acceleration. Without air resistance, objects fall at the same rate as seen in a vacuum. On Earth, however, it plays a crucial role in everything from weather patterns to vehicle design. Airplanes rely on controlled air resistance for lift, while meteors burn up due to extreme friction with the atmosphere. Work. In physics, work isn't about effort. It's about energy being transferred. Every time you push, pull, or lift an object, you're doing work by applying a force that moves something over a distance. If there's no movement, no matter how much effort is applied, no work is done. I feel exhausted, but if the wall doesn't move, no work has occurred in the physical sense. Work only happens when force results in displacement, like lifting a book from the floor to a shelf, kicking a ball, or pedaling a bicycle. The amount of work done depends on both the force applied and the distance moved. Lifting a heavy box to a high shelf requires more work than lifting a lighter box to the same height. Similarly, moving an object a longer distance increases the work done. Work also depends on direction. If force is applied in the same direction as motion, like pulling a cart forward, all energy goes into the work. But if force is applied at an angle, like pushing a box at a slant, only part of the effort contributes to movement. Work is crucial to understanding how energy flows through systems. It explains how engines function, how machines operate, and even how the human body moves. When work is done, energy is transferred, allowing systems to function. From powering massive industrial machines to something as simple as tossing a ball, every movement and every action transfers energy from one form to another. Work is energy in motion. It's the fundamental link between force and energy, driving the mechanics of the physical world. Energy. This is the currency of the universe. It fuels every motion, every transformation, every forced play. From the heat of the sun to the movement of your own body, energy is what makes anything happen. At its core, energy is the ability to do work. It exists in many forms: kinetic energy in moving objects, potential energy stored in stretched springs or elevated masses, thermal energy in heat, and chemical energy in food and fuel. While energy constantly changes form, it is never created or destroyed. This fundamental truth is known as the law of conservation of energy. Energy can be transferred or transformed, but the total amount in a closed system remains constant. Consider a roller coaster at the top of its track. It has maximum gravitational potential energy. As it descends, that stored energy transforms into kinetic energy, accelerating the coaster. Friction and air resistance turn some of that energy into heat, but no energy vanishes. It merely shifts from one form to another. Even the food you eat follows this rule. Chemical energy in food is converted into kinetic energy for movement, thermal energy to maintain body temperature, and electrical energy that powers nerve signals. Energy powers every system, from microscopic atoms to vast galaxies. Nuclear reactions convert mass into energy, fueling the sun. Electrical currents move through circuits, lighting entire cities. Even life itself depends on energy stored in molecules and released to keep organisms functioning. Everything in physics, from motion to forces, connects back to energy. It determines how objects move, collide, and change. Whether it's a falling apple or a star being born, energy is the thread that ties the universe together, shaping reality itself. Kinetic energy. Kinetic energy is the energy of motion. Anything that moves carries it, whether it's a falling raindrop, a speeding bullet, or a planet hurtling through space. Kinetic energy is what gives motion its power. The amount of kinetic energy an object has depends on two factors: mass and speed. A heavier object carries more kinetic energy than a lighter one moving at the same speed. But speed plays an even bigger role. When something moves twice as fast, its kinetic energy increases by much more than double. This is why a small pebble moving at high speed can still cause damage, while a massive boulder sitting still has no kinetic energy at all. Consider a car crash. A slow-moving car might dent a bumper, but a fast-moving car can cause complete destruction. The faster an object moves, the greater the energy it carries and the more impact it can have. This is why professional athletes, race cars, and even space shuttles are designed with an intense focus on motion. Harnessing kinetic energy can mean the difference between efficiency and failure. Kinetic energy doesn't just apply to objects we can see. It exists even at the microscopic level in the movement of molecules. The higher their kinetic energy, the hotter a substance becomes. This is why friction produces heat. Rubbing your hands together increases the motion of molecules, generating warmth. Kinetic energy is everywhere, from the movement of the smallest atoms to the largest celestial bodies. Understanding it helps explain everything from the mechanics of machines to the forces that shape the universe. Potential energy. Energy doesn't always need to be in motion to exist. Some energy remains stored, waiting for the right moment to be released. This is potential energy, the energy an object holds due to its position or condition. Whether it's a stretched rubber band, a compressed spring, or water behind a dam, potential energy is ready to transform into motion when the right force acts upon it. One of the most familiar forms is gravitational potential energy. A rock at the edge of a cliff isn't moving, but it holds energy due to its height. The higher the rock, the more potential energy it has. Once it falls, that stored energy converts into kinetic energy, powering its descent. Elastic potential energy works similarly. A slingshot stretched back holds energy in its tension. Release it, and that energy propels an object forward. Springs operate the same way. Whether compressed or stretched, they store energy that is unleashed when they return to their original shape. Chemical potential energy exists at the molecular level. The food you eat, the fuel in a car, or even explosives all contain stored energy in their chemical bonds. When triggered, this energy releases as motion, heat, or combustion. Potential energy allows energy to be stored and used precisely when needed, powering everything from hydroelectric dams to muscle movement. Recognizing its role helps explain how forces build up and how motion is controlled, shaping interactions from microscopic processes to the most powerful forces in the universe. Power. Power isn't just about force. It's about how quickly work is done. It measures the rate at which energy is transferred or converted, determining how efficiently something gets from one state to another. Whether it's a sprinter launching off the starting blocks or an engine driving a car, power dictates the speed of energy use. Imagine two people climbing a flight of stairs. One takes their time moving steadily, while the other rushes up in seconds. Both do the same amount of work, they lift their body weight up the same height, but the second person exerts more power because they complete the task in less time. Power isn't just about effort, it's about speed. This concept applies everywhere. A high-powered car accelerates faster because it delivers energy more rapidly to its wheels. A light bulb with more power shines brighter because it converts electrical energy into light at a faster rate. Even in nature, a roaring waterfall generates immense power as water crashes down, transferring energy rapidly to the rocks below. Power also determines efficiency. A machine that completes a task quickly with less wasted energy is more powerful than one that struggles and takes longer. That's why power ratings matter. From the wattage of a light bulb to the horsepower of an engine, they indicate how effectively energy is being used. At its core, power is about control over energy. It's not just about raw strength. It's about how efficiently and quickly energy flows. From the smallest circuits to the largest industrial systems, power drives the modern world, shaping everything from technology to transportation, turning potential into action in an instant. Conservation of energy. Energy never disappears. It only changes form. This is the principle of the conservation of energy, one of the most fundamental laws of physics. No matter what happens, the total amount of energy in a closed system remains constant. It cannot be created or destroyed, only transformed. Imagine a roller coaster at its highest point. At that moment, it holds energy in the form of potential energy stored due to its height. As it begins its descent, that energy transforms into kinetic energy, the energy of motion. The faster it moves, the more kinetic energy it has, but the total energy, potential plus kinetic, remains unchanged. Even friction and air resistance don't destroy energy. They simply convert some of it into heat. This principle applies to everything around us. A swinging pendulum moves back and forth, exchanging potential and kinetic energy with each swing until air resistance gradually converts some of that energy into heat. A car's fuel holds chemical energy, which is converted into motion, sound, and heat when the engine runs. Even the food we eat follows this rule. Our bodies convert chemical energy into movement, warmth, and biological processes. The conservation of energy governs everything from the smallest atomic reactions to the largest cosmic events. Stars burn by converting nuclear energy into light and heat. Even the expansion of the universe obeys energy conservation principles. This law sets a boundary for what's possible in physics. It tells us that no machine can create more energy than it consumes, and no event in nature happens without an energy transformation. Energy moves, shifts, and flows, but it never vanishes. Understanding this law isn't just about physics. It's about seeing the hidden exchanges that power the universe itself. Conservation of momentum. Momentum never vanishes, it only shifts. This is the principle of the conservation of momentum, a fundamental law of physics stating that in a closed system, the total momentum remains constant unless acted upon by an external force. It governs everything from the motion of planets to collisions on a billiard table. Momentum is the product of an object's mass and velocity. The larger or faster something moves, the more momentum it carries. But what makes this principle so powerful is that momentum isn't just something an object has, it's something that must be conserved. When two objects interact, they exchange momentum, but the total amount remains unchanged. Consider a simple collision. If two ice skaters push off each other, they move in opposite directions. Even though each skater changes speed, the total momentum before and after the push remains the same. The movement of one is perfectly balanced by the movement of the other. This principle applies at every scale. In space, where there's no friction, an astronaut throwing an object in one direction will move in the opposite direction. Rockets operate on this same principle. By expelling fuel at high speed, they propel themselves forward. Even high-speed crashes follow this rule. In car collisions, momentum is redistributed between vehicles with energy dissipated into sound, heat, and deformation. The conservation of momentum is absolute. It underlies Newton's laws and even extends into quantum mechanics. Every movement, every impact, every shift follows this unbreakable law, nature's way of ensuring perfect balance. Work-energy theorem. Energy doesn't just appear, it comes from work. This is the foundation of the work-energy theorem, which states that the work done on an object directly translates into a change in its energy. Whether speeding up a car, lifting a weight, or stopping a moving object, work and energy are two sides of the same equation. To understand this, imagine pushing a heavy box across the floor. The harder you push, the faster it moves. That effort, the force you apply over a distance, is work. And the result? The box gains kinetic energy. The more work you do, the more energy the box gains. Now consider slamming on the brakes of a moving car. The friction between the tires and the road does negative work, reducing the car's kinetic energy until it stops. Work doesn't just increase energy, it can take it away too. This relationship extends beyond simple motion. When lifting an object against gravity, you do work against the force pulling it down. That work is stored as potential energy, ready to be released when the object falls. Drop it, and that stored energy converts back into motion. The work-energy theorem connects force, motion, and energy into one principle. Whenever a force acts over a distance, it transfers energy. This concept explains everything from engines generating power to the way athletes build momentum. No work, no energy change. That's why the work-energy theorem is a cornerstone of physics. It reveals that energy isn't just a property, it's something that must be transferred through action. Every movement, every force applied, every shift in speed or height is work-shaping energy, fueling the mechanics of the universe. Center of mass. Balance a pencil on your finger, and you quickly find a single point where it remains stable. That point is its center of mass, the average position of all the mass in the object. It's the point where an object behaves as if all its mass is concentrated, making it essential for understanding motion, stability, and equilibrium. Every object has a center of mass, whether it's a simple ruler or a complex system like the human body. If you toss a wrench into the air, its individual parts may rotate unpredictably, but its center of mass follows a smooth, predictable path. This principle is why athletes, dancers, and engineers all rely on understanding it. Whether it's a gymnast adjusting midair, a rocket maintaining stability, or a vehicle staying upright during a turn, the center of mass is critical. The center of mass doesn't have to be inside the object. A hollow ring, for example, has its center of mass at the geometric center, where there's no actual material. In humans, it shifts with posture and movement. Standing upright, it's near the belly, but lean forward and it moves forward too. This concept is critical in physics and engineering. In architecture, buildings are designed with a low center of mass for stability. In space travel, rockets must have their center of mass carefully aligned to ensure controlled motion. Understanding the center of mass helps explain why objects topple, how forces act on a system, and how movement remains stable or chaotic. It's the unseen anchor of motion, defining how things balance, rotate, and move through space. Whether designing machines, predicting planetary orbits, or simply walking without falling, everything depends on this fundamental principle: center of gravity. Balance a pencil on your finger, and there's only one spot where it won't tip over. That point is its center of gravity, the location where an object's weight is perfectly balanced in all directions. Whether it's a spinning gymnast, a towering skyscraper, or a rolling car, the center of gravity determines stability and motion. The center of gravity, CG, is the average location of an object's weight distribution. For symmetrical objects like a sphere or cube, the CG is at the geometric center. But for irregular shapes, it shifts depending on how mass is spread. A hammer, for example, has its CG closer to the heavy metal head than the lighter handle. In everyday life, stability depends on the center of gravity. A low CG makes objects harder to tip over, which is why race cars hug the ground and wide-base structures like pyramids remain standing for centuries. When the CG moves beyond an object's base of support, it topples. This is why tightrope walkers carry long poles to lower their CG and maintain balance. In human movement, CG constantly shifts. When you stand, it's near your waist. When you bend forward, it moves outward, increasing the risk of falling. Athletes and performers train to control their CG for efficiency. Sprinters lean forward to shift their CG ahead, and ballet dancers adjust their limbs to maintain balance in midair. Engineers, architects, and designers all rely on the principles of CG to ensure safety and performance, from constructing bridges to designing backpacks that feel lighter. Understanding the center of gravity is crucial to mastering balance, stability, and control in the physical world. Rotational motion. Imagine spinning a bicycle wheel. The faster it turns, the harder it is to stop. This is rotational motion, the physics of objects that spin, rotate, and roll. Unlike linear motion, where objects move in a straight line, rotational motion describes movement around a fixed axis. At its core, rotational motion follows many of the same principles as linear motion, but with a twist, literally. Instead of position, we use angular displacement to describe how far something has rotated. Instead of velocity, we use angular velocity, which tells us how fast it's spinning. And instead of force, we use torque, the rotational equivalent of force. Moment of inertia. Imagine trying to spin a door by pushing near the hinges versus pushing at the edge. The difference in effort you feel is due to the moment of inertia, the rotational counterpart of mass in linear motion. It determines how much resistance an object has to changes in its rotation. Moment of inertia depends on two factors: the mass of an object and how that mass is distributed relative to the axis of rotation. The farther the mass is from the axis, the greater the moment of inertia. This is why a figure skater can spin faster by pulling their arms in. Reducing the distribution of mass decreases the moment of inertia, allowing rotation to speed up. Different shapes have different moments of inertia. A solid sphere rotates more easily than a hollow one of the same mass and radius because more of its mass is concentrated closer to the center. Similarly, a long rod spun about its center rotates more easily than the same rod spun about one end. Understanding moment of inertia is crucial in engineering and physics. In vehicles, flywheels store rotational energy by maximizing inertia, stabilizing motion. In sports, athletes adjust their body position to control spin, whether in gymnastics or diving. Even celestial bodies like planets and stars follow these principles in their rotational dynamics. Moment of inertia explains why some objects rotate easily while others resist. It governs everything from simple mechanical systems to the rotation of galaxies. By controlling the distribution of mass, we manipulate rotational motion, applying the same fundamental physics whether spinning a wheel, designing machinery, or launching spacecraft. Torque. Imagine trying to push open a heavy door. Where you apply force matters. Push near the hinges and the door barely moves. Push at the edge and it swings open easily. This is torque, the rotational equivalent of force. It determines how effectively a force can cause an object to rotate around an axis. Torque depends on three factors: the amount of force applied, the distance from the pivot point, and the angle at which the force is applied. The farther from the axis you push, the greater the effect. That's why wrenches have long handles. More distance from the pivot means more torque with the same effort. If the force is applied at an angle, only the component perpendicular to the lever arm contributes to rotation. A classic example of torque in action is a seesaw. If two people of equal weight sit at equal distances from the center, balance is maintained. But if one moves closer, their torque decreases, causing the other side to tip. Torque explains how levers work, from crowbars to bicycle pedals, amplifying small forces into powerful effects. In the natural world, torque governs the motion of planets, the rotation of gears, and the stability of bridges. Engineers rely on torque calculations to design everything from car engines to wind turbines, ensuring structures can withstand rotational forces without failure. Understanding torque is key to mastering rotational motion. Whether opening a door, tightening a bolt, or designing machinery, torque is the invisible force dictating how things turn, pivot, and move. It bridges everyday experiences with the deeper mechanics of physics, making the world's motion not just predictable but controllable. Angular momentum. Picture a figure skater spinning on ice. As they pull their arms in, they rotate faster without any external push. This is angular momentum in action, a fundamental principle that governs all rotating objects, from spinning tops to planets orbiting the sun. Angular momentum is the rotational equivalent of linear momentum. In linear motion, an object in motion stays in motion unless acted upon by an external force. Similarly, in rotational motion, an object keeps spinning unless an external torque acts on it. The key factors that determine angular momentum are an object's mass, its rotational speed, and how that mass is distributed relative to the axis of rotation. The most striking feature of angular momentum is its conservation. Unless an external torque interferes, angular momentum remains constant. This explains why a spinning skater speeds up when they pull their arms in. By reducing the distribution of mass around the axis, the rotation rate increases to compensate. The same principle applies to planets. When they move closer to the sun, they speed up, and when they drift farther away, they slow down. Angular momentum plays a crucial role in engineering, space exploration, and even nature. Gyroscopes, which rely on angular momentum, help stabilize ships, airplanes, and even smartphones. In space, astronauts use it to maneuver spacecraft without the need for external forces. Understanding angular momentum reveals why rotating objects behave the way they do, from a child's toy spinning on a table to the formation of entire galaxies. It's a concept that connects the smallest systems to the largest, demonstrating that motion, once set in motion, follows precise and unchanging laws. Conservation of angular momentum. A figure skater spins gracefully on the ice, arms extended. Then they pull their arms in and suddenly they spin faster. No external force acted on them, yet their rotation speed changed. This is the conservation of angular momentum, a fundamental principle governing rotational motion. Angular momentum is the rotational equivalent of linear momentum, describing how an object moves in a circular path. The key idea: if no external torque acts on a system, its angular momentum remains constant. This means that if one part of the system changes, like a skater pulling in their arms, the other part, in this case rotational speed, must adjust to compensate. Mathematically, angular momentum depends on an object's moment of inertia, its resistance to rotation motion, and its angular velocity, or how fast it spins. When the skater pulls in their arms, they reduce their moment of inertia, making it easier to rotate. To conserve angular momentum, their rotational speed must increase. This principle extends far beyond ice rinks. In space, where no external forces like friction act, it governs everything from planets to galaxies. When a collapsing star shrinks, its moment of inertia decreases, causing it to spin rapidly, sometimes forming a neutron star spinning hundreds of times per second. Even everyday objects obey this law. A spinning chair, a fidget spinner, or a bicycle wheel all demonstrate angular momentum conservation. Engineers use this principle in spacecraft design, adjusting rotation without thrusters by shifting mass within the craft. The conservation of angular momentum ensures that in any isolated system, rotation persists unless acted upon by an external force. Whether in sports, astrophysics, or engineering, understanding this principle unlocks deeper insights into how the universe moves. Centripetal force. Imagine swinging a ball on a string in a circle. The ball doesn't fly outward, it stays on its curved path. The force keeping it in motion isn't pulling outward, but inward. This inward force is known as centripetal force, and it's essential for any object moving in a circular path. Centripetal force acts perpendicular to an object's motion, constantly pulling it toward the center of rotation. Without it, the object would move in a straight line due to inertia. Think of a car turning around a curve. The friction between the tires and the road provides the centripetal force, preventing the car from skidding outward. If the road were icy and friction decreased, the car would struggle to stay on its curved path. In planetary motion, gravity acts as the centripetal force keeping planets in orbit around the Sun. Instead of flying off into space, Earth's motion is continually redirected inward due to the Sun's gravitational pull. Similarly, the Moon stays in orbit around Earth because of this same principle. The strength of centripetal force depends on three factors: the object's mass, its speed, and the radius of the circular path. A heavier object or faster speed requires a greater inward force to maintain circular motion. Likewise, decreasing the radius, like pulling a spinning skater's arms inward, demands a stronger force. Centripetal force is everywhere, from the curves of racetracks to the orbits of galaxies. Whether in engineering, sports, or celestial mechanics, controlling this force is key to maintaining stability in motion. It's what keeps satellites in orbit, roller coasters on their tracks, and planets locked in their cosmic dance. Simple machines. Lifting a heavy object, opening a door, or even cutting paper, these everyday actions rely on simple machines. These are fundamental devices that make work easier by amplifying force or changing its direction. Despite their simplicity, these machines form the foundation of nearly all mechanical systems. There are 6 classic types of simple machines. The lever consists of a rigid bar pivoting on a fulcrum. A seesaw, crowbar, or even a bottle opener uses this principle, applying force on one side to lift an object on the other. The pulley changes the direction of force using a rope and wheel, making it easier to lift heavy loads, as seen in cranes and flagpoles. The wheel and axle reduces friction, allowing motion with less effort, found in everything from bicycles to doorknobs. The inclined plane is a sloped surface that reduces the effort needed to raise objects. A ramp is easier to walk up than lifting a heavy object straight up. The wedge converts force into splitting action, like an axe or a knife. The screw is essentially an inclined plane wrapped around a cylinder, transforming rotation force into linear motion, securing objects or lifting materials. Simple machines don't generate energy. They redistribute force over distance, making tasks more manageable. A longer ramp means less effort, but a greater distance to travel. A lever with a well-placed fulcrum magnifies effort, allowing a small force to move a heavy object. Engineers combine simple machines into complex systems. Gears, engines, and construction tools all derive from these basic principles. Understanding them provides insight into the mechanics of motion, force, and efficiency, forming the basis of countless innovations throughout history. Whether ancient civilizations or modern technology, simple machines shape the way we interact with the physical world. Mechanical advantage. Lifting a heavy boulder with your bare hands is nearly impossible. But with a well-placed lever, the task becomes manageable. This is mechanical advantage, the principle that allows simple machines to amplify force, making work easier by redistributing effort. Mechanical advantage is a ratio that compares the output force a machine provides to the input force applied. In essence, it tells us how much a machine multiplies our effort. A crowbar, for example, allows a small applied force to lift something heavy by increasing the distance over which the force is exerted. Different machines achieve mechanical advantage in different ways. A lever, depending on the position of the fulcrum, can either multiply force or increase speed. A pulley system reduces the effort needed to lift an object by spreading the force over multiple ropes. An inclined plane allows heavy objects to be moved with less effort by extending the distance over which force is applied. In each case, the work done remains the same, but the force needed to complete the task decreases. A key concept in mechanical advantage is trade-off. While machines reduce the force required, they often increase the distance over which the force is applied. A long ramp requires less effort to push an object up, but the distance traveled increases. A pulley system cuts the effort in half, but requires pulling twice the rope length. Mechanical advantage forms the foundation of engineering and mechanics, influencing everything from construction cranes to bicycles and gears. By understanding how force is manipulated, engineers design tools, machines, and structures that make modern life possible. Whether lifting, cutting, or moving, mechanical advantage ensures that small efforts can achieve great results. Oscillations. A swing moving back and forth. A plucked guitar string vibrating. A clock's pendulum ticking away. These are all examples of oscillations, one of the most fundamental motions in physics. An oscillation is any repetitive movement around a central position. It occurs when an object is displaced from equilibrium and experiences a restoring force pulling it back. But instead of stopping at equilibrium, the object overshoots, moving in the opposite direction, repeating the process in a rhythmic cycle. A classic example is a mass on a spring. When stretched and released, the mass oscillates up and down. The further it moves from its resting position, the stronger the restoring force that pulls it back. This interplay between force and displacement drives oscillatory motion. Oscillations are categorized based on their nature. Mechanical oscillations include systems like pendulums and vibrating strings. Electromagnetic oscillations, such as alternating currents, involve energy shifting between electric and magnetic fields. Quantum oscillations even appear at atomic scales, governing the behavior of particles. Two key properties define an oscillation: period and frequency. The period is the time it takes to complete one full cycle. Frequency is how many cycles occur in a given time, typically measured in hertz, Hz. A high-frequency oscillation has many cycles per second, while a low-frequency one has fewer. Oscillations are everywhere. They describe the vibration of molecules in solids, the back and forth of sound waves, and the cycles of electrical signals in circuits. In music, oscillations create notes and tones, with frequency determining pitch. Engineers design systems to control or exploit oscillations, from the shock absorbers in cars damping mechanical oscillations to the precise timing of electronic circuits in computers. Even in nature, biological rhythms like heartbeats and circadian cycles are forms of oscillatory behavior. Understanding oscillations is essential in physics, engineering, and daily life. They reveal how systems respond to forces, how energy moves, and how stability is maintained or disrupted. Whether it's the gentle sway of a bridge in the wind or the complex vibrations in an earthquake, oscillations are a fundamental way the universe moves and responds to change. The period is the time for one full cycle, while frequency measures how many cycles occur per second. These values depend on factors like mass, stiffness, or length in mechanical systems. Oscillations are everywhere, from the beating of a heart to the waves of light and sound. They form the backbone of countless technologies, from timekeeping devices to radio signals. By understanding oscillatory motion, we unlock deeper insights into nature's repeating patterns, allowing us to harness their power in engineering, communication, and science. Simple harmonic motion. A pendulum swings back and forth. A mass bobs up and down in a spring. A child on a swing moves rhythmically. These are all examples of simple harmonic motion, SHM, one of the most fundamental types of repetitive motion in physics. SHM occurs when an object oscillates around an equilibrium position under the influence of a restoring force. This force always acts to pull the object back to its original position and is directly proportional to how far the object has been displaced. The further it moves, the stronger the force pulling it back. Consider a spring. When you stretch it and let go, the spring pulls the mass back toward the center. But because of momentum, the mass overshoots, stretching the spring in the opposite direction. This continuous back and forth motion defines SHM. The same principle applies to a pendulum. Gravity acts as the restoring force, pulling it back to the lowest point, only for it to swing past and repeat. A key feature of SHM is its periodicity. The motion repeats in regular time intervals. The time taken for one complete cycle is called the period, while the number of cycles per second is the frequency. The speed of oscillation depends on factors like mass and the stiffness of the spring or the length of the pendulum. SHM is everywhere, from the vibrations of atoms to the motion of planets in small perturbations. It's the foundation of countless real-world systems, from clocks to musical instruments. Understanding it allows us to design stable structures, efficient machines, and even predict the behavior of waves and sound. Whether microscopic or cosmic, the universe moves to the rhythm of simple harmonic motion. Wave concept. A stone drops into a still pond and ripples spread outward in perfect circles. A gust of wind bends a field of tall grass in rhythmic waves. Sound travels through air, reaching your ears as a melody. These are all examples of waves, one of the most fundamental ways energy moves through the universe. A wave is a disturbance that transfers energy through a medium or space without permanently displacing the particles within it. Instead of carrying matter, waves transmit energy by causing oscillations. These oscillations can be in different forms, leading to two main types of waves: mechanical and electromagnetic. Mechanical waves like sound, water waves, and seismic activity need a medium, air, water, or solid ground, to travel. They move in two ways: longitudinal waves, where the disturbance moves parallel to the wave's motion, and transverse waves, where the disturbance moves perpendicular to the wave direction. Electromagnetic waves like light, radio signals, and X-rays require no medium at all. They can travel through the vacuum of space, making them responsible for everything from the warmth of the sun to the signals in your phone. Waves are defined by properties such as wavelength, frequency, and amplitude. The wavelength is the distance between two wave peaks. Frequency measures how many cycles occur per second. Amplitude determines the wave's energy. From the smallest vibrations of atoms to massive ocean swells, waves govern how energy moves through the world. They are the foundation of sound, vision, communication, and even quantum mechanics. Understanding waves allows us to harness their power in everything from music to medical imaging, revealing the deep connections between motion, energy, and information. Frequency. A hummingbird flaps its wings so rapidly that they blur from sight. A high-pitched whistle pierces the air, while a deep drum beat shakes the ground. These seemingly different phenomena share a common thread: frequency, the rate at which something repeats over time. In physics, frequency is the number of cycles of a repeating event per unit of time. It tells us how fast something oscillates or vibrates, whether it's sound waves, light waves, or even the ticking of a clock. Frequency is everywhere. It is measured in hertz, where 1 hertz equals 1 cycle per second. Consider a swinging pendulum. If it completes one full back and forth motion every second, its frequency is 1 hertz. If it swings faster, completing 5 cycles per second, the frequency increases to 5 hertz. The same principle applies to waves. whether they are in water, sound, or light. In sound, frequency determines pitch. A low-frequency wave produces a deep bass note, while a high-frequency wave creates a sharp, high-pitched sound. Light behaves similarly. Higher frequencies correspond to blue and violet hues, while lower frequencies appear red. Beyond everyday experiences, frequency plays a role in radio signals, quantum mechanics, and even biological rhythms. Heartbeats, brainwaves, and electromagnetic radiation all operate at specific frequencies. Understanding frequency allows us to control and manipulate waves in technology, from wireless communication to medical imaging. It defines how energy moves through the universe, shaping the way we perceive and interact with the world. Period. A clock pendulum swings back and forth. A child on a swing moves in rhythmic motion. Ocean waves roll onto the shore in steady succession. Each of these motions follows a repeating cycle, and the period is what measures the time it takes for one complete cycle to occur. In physics, period is the time required for a repeating event to complete one full cycle. Whether it's a swinging pendulum, a vibrating guitar string, or the orbit of a planet, period defines how long it takes to return to the starting point. It is measured in seconds per cycle. Imagine a Ferris wheel. If it takes 30 seconds for one full rotation, that is its period. If the wheel speeds up and completes a full rotation in 15 seconds, the period decreases. This concept applies across all forms of oscillatory motion, from mechanical vibrations to electromagnetic waves. Period and frequency are closely related. While frequency tells us how many cycles occur in a second, period tells us how long each cycle takes. They are inversely proportional. A high-frequency wave has a short period, while a low-frequency wave has a long period. In everyday life, period helps us understand rhythmic motion, heartbeats, sound waves, and even the blinking of traffic lights. It plays a critical role in engineering, music, astronomy, and wave mechanics. By understanding period, we gain insight into how systems behave over time. Whether in the ticking of a clock or the orbit of celestial bodies, the concept of period allows us to quantify and predict the natural rhythms that govern motion across the universe. Wavelength. Imagine standing at the edge of a calm lake, tossing a pebble into the water. The ripples spread outward in perfect repeating patterns. The distance between two consecutive peaks of these ripples is what we call wavelength, a fundamental property of waves that determines their behavior across physics. Wavelength is the physical distance between two identical points in a wave cycle, whether it's from crest to crest in an ocean wave, peak to peak in a sound wave, or one full oscillation in a light wave. It plays a key role in defining how waves interact with the world. In light waves, wavelength dictates color. The longer the wavelength, the redder the light. The shorter, the bluer. Radio waves with wavelengths as long as skyscrapers carry signals invisibly across vast distances. Meanwhile, X-rays with wavelengths shorter than an atom penetrate flesh but are blocked by bone, making medical imaging possible. In sound waves, wavelength determines pitch. A low-frequency, long-wavelength wave produces a deep rumbling bass, while a short-wavelength wave results in a high-pitched tone like a whistle. Wavelength also governs how waves interact with obstacles. Longer wavelengths bend around barriers, explaining why we can hear sounds from around corners. Shorter wavelengths, like visible light, travel in straight lines and cast sharp shadows. Understanding wavelength is crucial in fields from communication to quantum physics. It defines how we see, hear, and experience the universe. Whether controlling the color of the sky, the tune of a song, or the function of a radio, wavelength is one of the invisible rulers shaping reality. Amplitude. A crashing ocean wave. The deep thud of a drum. The flickering brightness of a star. All of these are driven by amplitude, the measure of how intense or powerful a wave is. Whether it's sound, light, or motion, amplitude determines the strength of the wave. In physics, amplitude is the maximum displacement from a wave's rest position. It represents how far a vibrating object moves from its equilibrium. Imagine a child on a swing. If they barely move, the swing's amplitude is small. But if they soar high, the amplitude is large. The greater the amplitude, the more energy the wave carries. In sound waves, amplitude determines loudness. A whisper has a small amplitude, while a thunderclap has a much larger one. The same applies to light waves. Higher amplitude means greater brightness, while lower amplitude results in dimmer light. In seismic waves, amplitude defines the intensity of an earthquake. Small tremors produce barely noticeable movements, but large amplitudes can cause buildings to collapse. Amplitude is also crucial as encoding in radio signals and electronic waves. Stronger amplitude means clearer signals, which is why adjusting the amplitude in broadcasting changes the strength of transmission. Unlike frequency, which affects pitch or color, amplitude influences intensity. Two waves with the same frequency can have very different amplitudes, meaning they oscillate at the same rate but carry different amounts of energy. From the ripples in a pond to the vibrations in an earthquake, amplitude is a fundamental property of waves that controls the power behind motion, sound, and light. It is what makes waves not just move but matter. Wave speed. Picture yourself watching waves crash onto the shore. Some roll in slowly while others race ahead, reaching the beach in a rapid succession. The speed at which a wave travels is known as wave speed, a fundamental concept that determines how energy moves through different mediums. Wave speed is the rate at which a wave propagates through space or a material. It depends on two key factors: the wavelength, the distance between wave crests, and the frequency, how often those crests pass a given point. The greater the wavelength or the higher the frequency, the faster or slower the wave moves, depending on the medium. Consider sound waves in air. They travel at around 343 m/s, but in water, they move nearly 4 times faster. In solid materials like steel, they can reach speeds exceeding 5,000 m/s. This happens because molecules in solids are more tightly packed, allowing vibrations to transfer more efficiently. In light waves, wave speed takes on a universal limit: the speed of light in a vacuum, approximately 300,000 km/s. When light enters denser materials like glass or water, it slows down due to interactions with atoms, bending in the process, a phenomenon known as refraction. Ocean waves behave differently. Their speed is influenced by depth and gravity. In deep water, longer wavelengths move faster, creating the smooth, rolling swells seen far from shore. As they approach shallower regions, they slow down, increasing in height before breaking. Understanding wave speed is essential in fields from seismology to telecommunications. It dictates how earthquakes are detected, how signals travel through fiber optic cables, and even how astronomers study distant galaxies. Whether through air, water, or space, wave speed shapes how energy and information move across the universe. Sound waves. Sound is all around us, shaping the way we experience the world, from a distant thunderclap to the subtle creak of a floorboard. Every noise we hear is carried by sound waves, vibrations traveling through air, water, or solid matter. But what exactly is a sound wave, and how does it reach your ears? At its core, sound is the result of particles moving in a medium. When an object vibrates, whether it's a plucked guitar string or a speaker cone, it disturbs the air molecules around it, creating alternating regions of compression and rarefaction. These fluctuations in pressure propagate outward in all directions, forming a wave that carries energy through the medium. Unlike light, which can travel through empty space, sound needs a medium to exist. In the vacuum of space, there are no air molecules to transmit vibrations, making sound impossible. However, in dense materials like water or metal, sound travels faster because particles are more tightly packed, allowing energy to transfer more efficiently. The speed of sound depends on the medium. In dry air at room temperature, it moves at about 343 m/s. In water, it's nearly 5 times faster, and in steel, it reaches over 5,000 m/s. Sound waves also vary in frequency, the number of vibrations per second. Higher frequencies produce high-pitched sounds like a whistle, while lower frequencies create deep, rumbling tones. This range from low bass to high treble defines the way we perceive sound, from music to speech to sonar technology. Sound waves influence nearly every aspect of our lives. Whether carrying voices across a room or traveling vast distances through the ocean, they are one of the most essential ways the physical world communicates. Resonance. A small push at just the right moment can set something into powerful motion. This is the essence of resonance, a phenomenon where an object or system vibrates with increasing amplitude when exposed to periodic forces at its natural frequency. From musical instruments to collapsing bridges, resonance appears across physics, engineering, and everyday life. Every object has a natural frequency, the specific rate at which it naturally vibrates when disturbed. When an external force matches this frequency, energy is absorbed efficiently, causing the vibrations to grow stronger. A classic example is pushing a swing. If each push timed perfectly with the swing's motion, the oscillations increase dramatically with little effort. Resonance plays a crucial role in acoustics. When you pluck a guitar string, the soundboard vibrates in sync with the string, amplifying the sound. In wind instruments, air columns resonate at precise frequencies, shaping musical notes. In structural engineering, resonance can be destructive. The Tacoma Narrows Bridge disaster of 1940 is a famous case. Strong winds induced oscillations that matched the bridge's natural frequency, causing it to twist violently and collapse. This highlighted the importance of designing structures to withstand unintended resonance effects. Beyond mechanics, resonance is vital in electrical circuits. LC circuits, combinations of inductors and capacitors, resonate at specific frequencies, enabling radio tuning and signal processing. In atomic physics, magnetic resonance is the basis of MRI scans, where precise frequencies manipulate atomic nuclei to create detailed images of the human body. Resonance is everywhere, amplifying waves of energy when conditions align perfectly. Whether producing sound, powering technology, or shaping natural forces, resonance demonstrates the immense impact of timing and frequency in the physical world. Pressure. Every time you step on the ground, fill a balloon, or dive underwater, you're interacting with pressure, the force applied over a given area. It's an invisible yet fundamental force shaping everything from the air we breathe to the way fluids move. At its core, pressure is the amount of force exerted per unit area. Imagine pressing a finger against your palm. Now push with the same force using a sharp needle. The needle exerts far more pressure because the force is concentrated on a much smaller area. This is why knives cut, and why high heels can leave deep marks on soft surfaces. In fluids, pressure behaves uniquely. Pascal's principle states that in an enclosed fluid, pressure is transmitted equally in all directions. This is the reason hydraulic systems work. By applying force to one part of a confined liquid, the pressure spreads throughout, enabling massive forces to be controlled with minimal effort. It's the same principle that allows car brakes and hydraulic lifts to function efficiently. In gases, pressure is tied to molecular motion. Air molecules are constantly moving, colliding with surfaces, and exerting force. When you pump air into a tire, you're increasing the number of molecules inside, which collide more frequently, raising the pressure. Atmospheric pressure is another key factor. At sea level, the weight of the air above creates a significant force. As you climb a mountain, the thinner air means lower pressure, which is why sealed bags expand at high altitudes. Understanding pressure helps explain weather patterns, deep sea diving, and even why planes fly. It governs how gases, liquids, and solids interact, making it a crucial concept in physics, engineering, and everyday life. Fluid statics. Imagine diving into a swimming pool. As you descend, you feel the pressure build around you. This is fluid statics in action, the study of fluids at rest and the forces they exert. Whether it's the pressure at the bottom of the ocean, the buoyancy keeping ships afloat, or the atmospheric weight pressing down on us, fluid statics explains how still fluids behave under force. One of the key principles of fluid statics is pressure in a fluid. In a container, a fluid exerts pressure in all directions, increasing with depth. This is why the walls of a dam are thicker at the bottom. They must withstand greater pressure from the water above. The equation for pressure in a fluid shows that pressure depends on depth, density, and gravity, not the shape of the container. A crucial effect of this pressure is buoyancy, discovered by Archimedes. When an object is submerged in a fluid, it experiences an upward force equal to the weight of the fluid it displaces. This is why heavy steel ships float while a solid steel ball sinks. If the buoyant force is greater than the object's weight, it rises. If less, it sinks. Fluid statics also explains Pascal's principle, which states that a pressure change in a confined fluid is transmitted equally in all directions. This principle is the foundation of hydraulic systems, allowing small forces to lift massive objects, from car brakes to construction machinery. From submarines balancing buoyancy to the air pressure affecting weather patterns, fluid statics governs many unseen forces shaping our world. Understanding these principles helps engineers, scientists, and designers harness the power of fluids, whether in deep-sea exploration or everyday hydraulic machines. Fluid dynamics. Water rushing through a river, air swirling around an airplane wing, blood flowing through veins. These are all governed by fluid dynamics, the study of how fluids move. Unlike fluid statics, which deals with fluids at rest, fluid dynamics explains motion, turbulence, and flow patterns that shape everything from weather systems to engineering marvels. One of the key ideas in fluid dynamics is streamline flow versus turbulent flow. In streamline or laminar flow, fluid moves smoothly in parallel layers, like oil flowing through a pipe. In turbulent flow, chaos takes over. Eddies, swirls, and vortices form, like wind gusting around a building or water crashing over rocks at a river. Whether a fluid flows smoothly or turbulently depends on factors like speed, viscosity, and obstacles in its path. A crucial principle governing fluid motion is Bernoulli's principle. It states that as a fluid's speed increases, its pressure decreases. This explains how airplanes stay in the air. Air moves faster over the curved top of the wing, creating lower pressure and generating lift. The same principle helps spray bottles work, as moving air lowers pressure, pulling liquid upward. Another key idea is continuity of flow, which states that fluid speed changes with pipe size. A wide river slows down, while a narrow nozzle speeds water up, like a thumb partially blocking a garden hose. This is why blood moves faster in narrow arteries than in wider veins. From weather patterns to car aerodynamics, fluid dynamics shapes the world around us. Engineers and scientists use these principles to design everything from efficient water systems to aircraft, harnessing the power of moving fluids to improve technology, transportation, and even medicine. Understanding fluid dynamics reveals the invisible forces guiding motion in both nature and technology. Viscosity. Imagine pouring honey and water side by side. The water flows effortlessly, but the honey moves sluggishly, stretching into thick, slow-moving streams. This difference in flow is due to viscosity, the measure of a fluid's resistance to motion. Viscosity describes how easily a fluid flows. Low-viscosity fluids like water or air move freely, while high-viscosity fluids like honey or lava resist motion and flow much more slowly. This resistance comes from internal friction between the molecules of the fluid. In a high-viscosity fluid, the molecules interact strongly, resisting movement. In a low-viscosity fluid, these interactions are weaker, allowing for smoother motion. Temperature also affects viscosity. Heating honey makes it flow more easily because increased temperature reduces molecular interactions. This is why oil in a car engine becomes thinner when warm, improving lubrication. Conversely, colder temperatures increase viscosity, thickening fluids and making them hard to move. Viscosity is critical in countless applications. Engineers consider it when designing pipelines to ensure liquids flow efficiently. It determines how lubricants reduce friction in machines, preventing wear and overheating. In food production, Controlling viscosity ensures the right texture in products like sauces or syrups. Nature also relies on viscosity. Blood has an optimal viscosity to flow through veins and arteries without clotting or moving too slowly. Lava's viscosity determines whether it oozes slowly or explodes violently from a volcano. Even air has viscosity, affecting how objects move through it and contributing to drag on airplanes and cars. Understanding viscosity reveals the hidden resistance within fluids, shaping how they move, interact, and perform essential roles in technology, industry, and life itself. Temperature plays a key role in viscosity. When honey is heated, it flows more easily because the molecules move faster and interact less. Similarly, cold engine oil thickens, making it harder for an engine to function smoothly. This is why motor oils are designed to perform across a range of temperatures, ensuring proper lubrication under different conditions. Viscosity also affects how objects move through fluids. In a swimming pool, moving your hand through water is easy, but doing the same in a pool of syrup would require much more effort. This resistance is why some animals, like penguins and dolphins, have evolved streamlined bodies to reduce drag and move efficiently through water. In practical applications, viscosity is crucial in industries ranging from food production to medicine. It determines how smoothly paint spreads, how fuel flows in engines, and even how blood circulates in the body. Understanding viscosity helps explain the behavior of fluids in nature and technology. It governs how liquids and gases move, making it a fundamental concept in physics, engineering, and everyday life. Temperature. Touch a metal railing on a hot day and it burns. Hold an ice cube and your fingers go numb. These sensations are all about temperature, a measure of how hot or cold something is. But what is temperature really? At its core, temperature is a measure of the average kinetic energy of the particles in a substance. When particles move faster, they have more energy and the temperature rises. When they slow down, the temperature drops. It's not about the size or amount of the object, just how much motion is happening at the microscopic level. Temperature is measured using different scales. The Celsius scale is commonly used worldwide, where water freezes at 0 degrees and boils at 100 degrees. The Fahrenheit scale, used mainly in the US, sets these points at 32 degrees and 212 degrees. Scientists, however, rely on the Kelvin scale, where absolute zero, the lowest possible temperature where molecular motion nearly stops, is set at 0 Kelvin. Heat and temperature are closely related but not the same. Heat is energy transfer due to temperature difference, while temperature itself is just a measurement of energy. A bathtub of warm water contains more total heat energy than a cup of boiling water, even though the cup is hotter, because the bathtub holds far more water molecules. See, temperature governs everything from weather patterns to chemical reactions. In space, temperatures plummet to extremes, while inside stars, nuclear fusion drives heat beyond imagination. Even on Earth, life depends on temperature balance. Our bodies regulate heat to function efficiently. Understanding temperature is essential in physics, engineering, and everyday life. Whether cooking, driving, or even feeling the warmth of the sun, temperature is a fundamental part of how we experience and interact with the world. Heat. Heat is energy in motion. It's what makes metal glow in a forge, water boil in a pot, and ice melt in your hand. But heat isn't a substance. It's the transfer of thermal energy from one place to another. At the atomic level, everything is in motion. The faster the atoms and molecules move, the more energy they have. Heat flows when this energy is transferred from a hotter object to a cooler one. This happens in 3 main ways: conduction, convection, and radiation. Conduction occurs through direct contact. When you touch a hot pan, heat flows from the metal to your skin, because fast-moving particles collide with slower ones, transferring energy. Metals conduct heat efficiently because their atoms are tightly packed, allowing energy to move quickly. Convection happens in fluids, liquids, and gases, where warmer, less dense regions rise while cooler, denser regions sink. This cycle creates currents, like the movement of air in the atmosphere or the circulation of water in a heated pot. Radiation doesn't require contact or a medium. The sun warms Earth through electromagnetic waves carrying energy across space. This is why you feel warmth from a fire, even if you're not touching it. Unlike temperature, which measures the average energy of particles, heat measures total energy transfer. A spark from a match may be hot, but it carries far less heat than a cup of warm water because it has fewer particles. Heat plays a crucial role in nature and technology. It drives weather systems, powers engines, and enables life on Earth. Understanding heat allows us to harness its power, from cooking food to generating electricity, making it one of the most essential forms of energy transfer in the universe. Zeroth law of thermodynamics. Imagine holding a cup of hot coffee. Over time, the heat spreads, making the cup warm and the coffee slightly cooler. Eventually, both reach the same temperature. This simple observation leads to one of the most fundamental principles of thermodynamics, the Zeroth law. The Zeroth law of thermodynamics states, if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In other words, if object A is at the same temperature as object C, and object B is also at the same temperature as object C, then A and B must be at the same temperature. This might seem obvious, but it's the foundation of how we define and measure temperature. Consider a thermometer. When placed in contact with a substance, the thermometer liquid or sensor adjusts until it reaches thermal equilibrium with the substance. Because of the Zeroth law, we trust that the thermometer reading accurately reflects the temperature of what it's measuring. This law is fundamental because it establishes temperature as a meaningful and measurable quantity. Without it, we wouldn't have a consistent way to compare temperatures, making thermodynamics and much of modern science impossible. The Zeroth law is deceptively simple but essential. It ensures that heat flows predictably, allowing us to understand energy transfer, design engines, and regulate climates. It's the reason you can trust a thermostat, the reason heat spreads evenly, and the principle that defines the very concept of temperature. First law of thermodynamics. Energy cannot be created or destroyed, only transferred or transformed. This fundamental principle lies at the heart of the first law of thermodynamics, a cornerstone of physics that governs everything from the motion of planets to the way your car engine works. The first law of thermodynamics states that the total energy of an isolated system remains constant. Energy can change forms. Heat can become mechanical work, chemical energy can become electrical energy. But the total amount of energy always stays the same. This law is essentially a statement of energy conservation. Imagine a hot cup of tea. Over time, heat energy from the tea transfers into the surrounding air, cooling the liquid. But where does that heat go? It does disappear. It spreads into the environment, warming the air molecules. Similarly, when you eat food, the chemical energy stored within it is converted into kinetic energy when you move, thermal energy when you stay warm, and even electrical signals in your brain. The first law also explains how engines work. When fuel burns in a car engine, chemical energy transforms into heat, which is then converted into mechanical work, propelling the car forward. Not all energy becomes useful work. Some is always lost as heat, which is why no machine is 100% efficient. This principle governs every energy exchange in the universe, from biological metabolism to industrial power plants. Every process follows the first law, ensuring that while energy constantly shifts from one form to another, its total amount remains unchanged. Whether it's the sun warming the earth or a battery powering a phone, energy is never lost, just rearranged. Second law of thermodynamics. Left on its own, everything tends toward disorder. Ice melts, batteries drain, and stars burn out. This is the second law of thermodynamics, one of the most fundamental principles of physics, governing the direction of all natural processes. At its core, the second law states that in any energy transfer or transformation, the total entropy of a system and its surroundings will always increase. Entropy is a measure of disorder or randomness. A highly ordered system, like a neatly stacked pile of books, has low entropy. But if the books fall to the floor in a scattered mess, entropy has increased. The universe naturally moves toward higher entropy. Consider heat flow. A hot cup of coffee left in a room will cool down, while the surrounding air slightly warms up. Heat energy spreads out, never spontaneously concentrating back into the coffee. This one-way direction of heat transfer, from hot to cold, is an irreversible process dictated by the second law. This principle explains why machines are never 100% efficient. Some energy is always lost as heat, dissipating into the surroundings. Even living organisms must constantly consume energy to counteract entropy and maintain order. On a cosmic scale, the second law predicts the eventual fate of the universe. Over immense timescales, all energy will spread out, stars will burn out, and the cosmos will reach a state of maximum entropy, often referred to as heat death. From engines to ecosystems, every system follows this rule. Energy disperses, structures break down, and disorder grows. The second law of thermodynamics defines the arrow of time itself, ensuring that while energy remains constant, its ability to do useful work is always decreasing. Third law of thermodynamics. Picture a world without movement, where atoms and molecules are completely still. This is the extreme scenario described by the third law of thermodynamics, which states that as a system approaches absolute zero, the lowest possible temperature, its entropy or disorder also approaches a minimum value. Absolute zero is the theoretical point at minus 273.15 degrees Celsius, 0 Kelvin, where all molecular motion would cease. According to the third law, as a substance gets colder, its particles lose energy and settle into a more ordered state. At absolute zero, a perfectly crystalline substance, one with no atomic defects or irregularities, would have zero entropy because there's no randomness left in its arrangement. Why does this matter? Because it sets a fundamental limit on temperature and energy. No matter how advanced our technology becomes, we can never actually reach absolute zero, only get infinitely close. The reason is simple: removing that last bit of heat energy would require an infinite amount of effort. The effects of this law can be seen in cryogenics and superconductors. As materials approach absolute zero, their electrical resistance can disappear entirely, leading to superconductivity, a state where electricity flows without energy loss. This is crucial for technologies like MRI machines and quantum computers. The third law of thermodynamics reinforces the concept that there's always a fundamental limit to how much disorder can be removed from a system. It defines the boundary of cold, shaping our understanding of low-temperature physics and proving that even in a universe dominated by entropy, there is a final, unreachable state of perfect order. Ideal gas. Gases may seem unpredictable, expanding, compressing, and flowing freely. But beneath this apparent chaos, their behavior follows a simple yet powerful rule: the ideal gas law. This fundamental principle describes the relationship between a gas's pressure, volume, and temperature, showing how they interact under different conditions. At its core, the ideal gas law states that if you change one property of a gas, the others must adjust accordingly. Heat a gas and its particles move faster, increasing pressure if volume is fixed. Expand the volume and pressure drops as particles have more space to move. Cool the gas and everything slows down, reducing both pressure and volume. These relationships explain why a balloon shrinks in cold weather, or why a sealed container might burst if heated. The ideal gas law is an approximation, assuming gas particles move freely and don't interact beyond simple collisions. While real gases deviate under extreme conditions, this law works remarkably well for everyday applications. It governs everything from weather patterns and engine performance to how your lungs function when you breathe. This law also helps scientists understand the behavior of gases in space, where pressure changes can cause dramatic expansions or compressions. It's why engineers designing spacecraft and deep-sea submersibles rely on gas laws to predict how materials will respond to changes in their environment. The ideal. Gas law is more than just an equation. It's a key to unlocking the hidden ore in gases, proving that even the most chaotic systems follow fundamental rules. Whether in laboratories, industrial processes, or the natural world, this law reveals the precise balance between pressure, volume, and temperature, making it an essential tool in physics and engineering. Kinetic theory of gases. Imagine a room filled with countless invisible particles moving chaotically, colliding with each other and the walls at incredible speeds. Though we can't see it, this microscopic chaos explains how gases behave. This is the kinetic theory of gases, a model that reveals how gas particles move and interact, forming the foundation of our understanding of pressure, temperature, and volume. At its core, the kinetic theory states that gases consist of tiny particles, atoms or molecules, in constant random motion. These particles move in straight lines until they collide, either with each other or with the walls of their container. These collisions are what create pressure. When gas particles strike a surface, they exert force. The more frequent and energetic the collisions, the higher the pressure. Temperature is directly linked to the motion of gas particles. When a gas is heated, its particles move faster, increasing both pressure and volume if the gas is allowed to expand. Conversely, cooling the gas slows down the particles, reducing their energy and lowering the pressure. The kinetic theory also explains why gases compress and expand so easily. Since most of a gas's volume is empty space, particles can be squeezed closer together under pressure or spread apart when pressure decreases. This principle is essential in everything from inflating balloons to understanding how airplane cabins maintain pressure at high altitudes. This theory isn't just an abstract idea. It's a tool used in engineering, meteorology, and even space exploration. It helps scientists predict how gases behave under different conditions, allowing for innovations in everything from combustion engines to climate modeling. By understanding the ceaseless motion of gas particles, we uncover the hidden dynamics shaping the world around us. Phase transitions. A block of ice melts into water. Water heats up and turns into steam. These transformations may seem simple, but they reveal one of the most fundamental principles in physics. Phase transitions. They describe how matter changes between solid, liquid, and gas states, governed by temperature and pressure. At the core of phase transitions is energy. Every substance is made of molecules constantly moving. In a solid, molecules are tightly packed, vibrating in place. As heat is added, they gain energy, breaking free from their rigid structure. This is melting, where a solid becomes a liquid. The reverse process, freezing, occurs when energy is removed, slowing molecular motion until they lock into place. Liquids have more freedom. Their molecules slide past one another, but with enough heat, they reach their boiling point where molecules gain enough energy to break away entirely and form a gas. This is evaporation. The reverse, condensation, happens when gas cools and molecules lose energy, clumping together into a liquid. Not all transitions happen between common phases. Under extreme conditions, matter enters states like plasma, where atoms are stripped of electrons, creating charged particles found in stars and lightning. There's also the mysterious Bose-Einstein condensate, where atoms near absolute zero behave as a single quantum entity. Phase transitions aren't just about ice melting in your drink. They explain weather patterns, power refrigeration, and even help scientists understand the behavior of matter at the smallest scales. From the water cycle to cutting-edge physics, these transformations reveal how energy shapes the physical world. Statics. A towering bridge, a skyscraper, or even a ladder leaning against a wall. What keeps them standing still? The answer lies in statics, the branch of physics that studies forces in equilibrium. When an object is at rest or moving at a constant velocity, the forces acting on it must be perfectly balanced. At the core of statics is Newton's first law, which states that an object remains at rest unless acted upon by an unbalanced force. In static systems, every force is counteracted by another, creating a stable structure. A suspension bridge, for instance, stays in place because the force of gravity pulling it downward is exactly balanced by the tension in the cables holding it up. Statics relies on two fundamental conditions for equilibrium. Translational equilibrium means that the sum of all forces acting on an object is zero, preventing any movement. Rotational equilibrium ensures that the sum of all torques is zero, preventing rotation. Imagine a seesaw with equal weights on both ends. It remains level because the forces and torques are balanced. Real-world applications of statics are everywhere. Architects use statics to design buildings that withstand wind and weight. Engineers apply it to bridges, cranes, and towers to ensure stability. Even something as simple as stacking books requires an understanding of balance and force distribution. Understanding statics allows us to predict how structures will behave under different conditions. Whether designing a skyscraper or just setting up a ladder, the principles of statics ensure that objects remain solid, secure, and unmoving. In a world shaped by forces, statics is what keeps everything in place. Statistical mechanics. At any moment, the air around you is filled with countless molecules moving in random directions, colliding and exchanging energy. Tracking each one individually is impossible, yet their collective behavior follows predictable patterns. This is the foundation of statistical mechanics. Statistical mechanics is the branch of physics that connects microscopic particle behavior to macroscopic properties like temperature, pressure, and entropy. Instead of studying each particle individually, it uses probability and averages to describe how large groups behave. At its core, statistical mechanics rests on the idea that while individual particles behave randomly, the overall system has predictable properties. For example, while the motion of a single gas molecule is chaotic, the pressure of the gas in a container remains stable and measurable. This approach allows physicists to derive fundamental laws of thermodynamics from molecular behavior. It explains why heat flows from hot to cold, why entropy increases, and how equilibrium is reached. Statistical mechanics also underpins the concept of entropy. In this framework, entropy measures the number of ways a system can be arranged while still having the same energy. More possible arrangements mean higher entropy. Beyond classical gases, statistical mechanics extends to solids, liquids, and even quantum systems. It explains why materials have specific heat capacities, how phase transitions occur, and why certain properties emerge only at very low temperatures. In modern science, statistical mechanics is essential. In fields ranging from materials science and chemistry to cosmology and quantum computing. By connecting the microscopic world of atoms and molecules to the macroscopic world we experience, statistical mechanics reveals the hidden order in apparent chaos, showing how the universe's complex behavior arises from simple, fundamental principles. A branch of physics that connects microscopic motion to large-scale properties like temperature, pressure, and entropy. Unlike classical mechanics, which describes the motion of individual objects, statistical mechanics deals with systems containing vast numbers of particles. It uses probability to determine how these particles behave on average, reveal patterns that emerge from apparent chaos. For example, the temperature of a gas isn't a property of any single molecule, but a measure of the average kinetic energy of all the molecules combined. One of the key ideas in statistical mechanics is entropy, the measure of disorder in a system. When energy spreads out like heat dissipating from a hot object to a cooler one, entropy increases. This statistical tendency toward higher entropy explains why natural processes such as melting ice or diffusing gases move in one direction rather than reversing spontaneously. Statistical mechanics also provides the foundation for understanding phase transitions. When water turns to steam, for example, it's not just a change in state, but a collective shift in molecular behavior governed by probability. The same principles apply to solids melting, magnets losing their alignment, or even superconductors operating at low temperatures. This approach extends to quantum mechanics, predicting electron distributions in atoms and behaviors of complex materials. By focusing on averages and probabilities, statistical mechanics transforms microscopic randomness into macroscopic predictability, forming the backbone of modern thermodynamics and material science. Electric charge. Every time you flip a switch, charge your phone, or feel a tiny shock from touching a doorknob, you're experiencing one of the most fundamental properties of the universe: electric charge. Electric charge is an intrinsic property of matter responsible for all electrical and magnetic interactions. It comes in two types: positive and negative. Opposite charges attract, while like charges repel. This simple rule governs everything from how atoms hold together to the forces behind lightning strikes. At the smallest scale, protons carry a positive charge, electrons carry a negative charge, and neutrons remain neutral. The balance of these charges determines how objects interact. When electrons move or transfer between objects, they create electric forces. That's why rubbing a balloon against your hair makes it stick to a wall. The balloon steals electrons, gaining a negative charge while your hair is left positively charged. Opposites attract, and the balloon clings. Electric charge is measured in coulombs, named after physicist Charles-Augustin de Coulomb, who quantified how charges interact. His work laid the foundation for understanding electrostatic forces, showing that the force between two charged objects depends on their charge strength and the distance between them. But charge doesn't just create static electricity. It drives electric currents. In metals, free electrons move through a conductor, creating electricity that powers everything from light bulbs to supercomputers. This movement of charge underpins modern technology, communication, and even life itself. Our nervous system relies on charged ions to send signals through the body. Electric charge isn't just a property of particles. It's the force shaping the world from the smallest electron to the largest thunderstorms. Mastering this concept unlocks a deeper understanding of electricity, magnetism, and the invisible forces that power our universe. Coulomb's law. Every interaction between charged objects follows a fundamental rule: an invisible force pulling them together or pushing them apart. This is Coulomb's law, the principle that governs electric forces at the smallest scales and across vast distances. Proposed by attraction or repulsion is strong, but pull them apart and the effect weakens. The same happens with electric charges. A positively charged particle attracts a negatively charged one, while two like charges repel each other, following the same predictable rule. This law is the foundation of electrostatics and applies everywhere. It explains why electrons stay bound to atomic nuclei, how charged particles move in electric fields, and why static electricity makes your hair stand on end after rubbing a balloon. Coulomb's law also plays a crucial role in technology, from the design of capacitors in circuits to the interactions between ions in chemistry. Understanding this force is essential. Even in deep space, the behavior of charged particles in plasma follows Coulomb's principles. Coulomb's law provides a precise and measurable way to predict and control electrostatic interactions, forming the basis for many applications in physics and engineering. Electric field. You can't see it, but it's everywhere. A force that reaches across space, affecting everything with an electric charge. This is the electric field, an invisible structure that dictates how charged objects interact, even when they never touch. An electric field is created by any charged object. It extends outward, influencing other charges in its vicinity, just like gravity pulls objects without direct contact. If you place a positive charge in an electric field, it feels a force pushing or pulling it depending on the field's direction. The strength of this force depends on the charge creating the field and the distance from it. To visualize this, imagine a charged object as a lit candle in a dark room. The light spreads in all directions just as an electric field extends outward. The closer you are, the stronger the effect. Move farther away and the influence fades. Electric fields follow predictable patterns. A positive charge produces a field that radiates outward, while a negative charge draws field lines inward. When multiple charges are present, their fields interact, forming complex patterns that dictate the movement of nearby particles. This invisible force is fundamental to countless phenomena. Lightning forms because of the intense electric fields between clouds and the ground. The screens on your phone respond to touch using electric fields to detect changes in charge. Even nerve signals in your body rely on tiny electric fields to transmit information. The electric field is not just a theoretical concept. It's an essential force shaping the world at every level. Understanding it allows us to manipulate electricity, build technology, and explore the hidden forces that govern our universe. Electric potential. Electric potential is the hidden energy behind every spark, every circuit, every charge in motion. It's the force that pushes electricity forward, shaping how charges move and interact. At its core, electric potential is the amount of energy per unit charge at a given point in an electric field. It tells us how much work is needed to move a charge from one place to another. Just like a ball at the top of a hill has gravitational potential energy, a charge in an electric field has electric potential energy. The higher the potential, the more energy available to move charges. To visualize this, imagine a waterfall. Water flows from a higher elevation to a lower one, driven by gravity. Similarly, electric charges move from high potential to low potential, driven by the electric field. The greater the difference in height, the stronger the water flow. Just like a greater difference in electric potential creates a stronger push for charge movement. This difference in electric potential is what we call voltage. It's what powers every electrical device, from your phone to massive power grids. When you plug in a device, you're connecting it to a voltage source, creating a pathway for electric charges to move. Electric potential is more than just a concept. It's the driving force behind electricity itself. It determines how charges behave, how energy is transferred, and how we harness electricity to power the modern world. Whether in batteries, circuits, or the natural world, understanding electric potential is key to understanding how electricity flows. Capacitance. Capacitance is the ability to store electric charge, a fundamental concept that powers everything from camera flashes to computer memory. At its simplest, capacitance measures how much charge a system can hold for a given voltage. This is achieved using a capacitor, an electrical component designed to store and release energy on demand. A capacitor consists of two conductive plates separated by an insulating material called a dielectric. When connected to a voltage source, electrons accumulate on one plate while the other plate becomes positively charged. This separation of charge creates an electric field, allowing the capacitor to store energy. To visualize this, imagine a water tank with a flexible membrane in the middle. As water is pumped in, one side fills while the other side empties, storing potential energy in the stretched membrane. Similarly, a capacitor holds electrical energy until it's needed. The capacitance of a capacitor depends on three factors: the surface area of the plates, the distance between them, and the properties of the dielectric material. Larger plates store more charge. Closer plates create a stronger electric field. Better dielectrics enhance storage capacity. Capacitors have countless applications. They smooth out voltage fluctuations in power supplies, help filter signals in audio and radio circuits, and provide the quick bursts of energy needed in camera flashes and electric vehicles. Unlike batteries, capacitors charge and discharge almost instantly, making them ideal for rapid energy storage. Understanding capacitance is key to mastering electrical circuits. Whether controlling energy flow in simple electronics or enhancing performance in advanced technology, capacitors are essential in shaping how we store and manage electrical energy. Ohm's law: electric current is the invisible force that powers the modern world. From the smallest circuits in your phone to massive power grids, everything runs on the movement of electric charge. At its core, electric current is the flow of charged particles, usually electrons, through a conductor. It's similar to water flowing through a pipe. Just as water moves from high pressure to low pressure, electric charges move from high potential to low potential when a voltage is applied. The amount of current depends on how easily charges can move through the material. This brings us to Ohm's law, the fundamental relationship between voltage, current, and resistance. It tells us that the current in a circuit is directly proportional to the voltage applied and inversely proportional to the resistance. Simply put, increase the voltage and more current flows. Increase the resistance and the current slows down. To understand this, imagine pushing water through a hose. Higher water pressure, voltage, pushes more water, current. But if the hose is narrow, higher resistance, less water can flow. The same principle applies to electricity. Higher voltage pushes more current, while higher resistance limits it. Every electrical device relies on this principle. Resistors control current flow. Circuit breakers prevent overloads. Conductors ensure smooth transmission of energy. Understanding electric current and Ohm's law is essential for everything from designing electronics to managing power distribution. It's the foundation of how electricity moves, how we control it, and how we harness it efficiently. Whether in simple circuits or complex electrical systems, these principles define how energy flows through our world. Basic circuit analysis. Every electronic device, from a flashlight to a supercomputer, relies on circuits to function. Understanding how circuits work is fundamental to grasping electricity itself. Circuit analysis is the method used to determine how voltage, current, and resistance interact within a circuit. At its core, a circuit is a closed loop through which electric current flows. If the loop is broken, the current stops, just like a water pipe with a missing section would fail to deliver water. A basic circuit consists of three key components. A voltage source, like a battery, which provides the push needed for electrons to move. Resistors, which limit current flow, similar to narrowing a water pipe. And conductors, the wires that carry electricity between components, much like roads guiding traffic. Circuit analysis is based on two fundamental laws. Ohm's law relates voltage, current, and resistance, telling us how much current will flow through a component based on the applied voltage and its resistance. Kirchhoff's laws help analyze circuits with multiple loops and branches. Kirchhoff's voltage law states that the sum of voltages around any closed loop must equal zero, ensuring energy is conserved. Kirchhoff's current law states that the total current entering a junction must equal the total current leaving, like cars merging into lanes on a highway. By applying these laws, we can calculate how current and voltage are distributed across complex circuits, ensuring proper function and safety. This analysis is crucial in designing everything from household wiring to microprocessors. Circuits are the foundation of modern technology. Understanding their behavior allows us to harness electricity efficiently, ensuring devices operate as intended. AC and DC electricity. Electricity powers everything around us, but not all electricity flows the same way. There are two main types: alternating current, AC, and direct current, DC. Understanding their differences is key to grasping how electricity works in everything from power grids to smartphones. Direct current, DC, is simple. It flows in one steady direction. Imagine a river moving smoothly downstream. The electrons travel in a straight path from the power source to the device. Batteries, fuel cells, and solar panels all produce DC electricity. Your phone, laptop, and most small electronics run on DC power because it provides a stable voltage. Alternating current, AC, on the other hand, is constantly changing direction. Instead of flowing straight like a river, it moves back and forth like ocean waves. This rapid switching happens many times per second, typically 50 or 60 times per second, Hertz, depending on the region. AC power is what runs through homes, businesses, and power grids because it can travel over long distances with minimal energy loss. The reason AC dominates large-scale electricity distribution is due to efficiency. When electricity is transmitted over power lines, high voltage is needed to reduce energy loss. AC voltage can be easily increased or decreased using transformers, making it ideal for long-distance transmission. DC, however, is harder to convert and loses energy more quickly over distance. But DC isn't obsolete. Modern advancements like high-voltage DC transmission and renewable energy systems rely on it. Most electronic devices use DC, which is why power adapters and chargers convert AC from wall outlets into DC. Both AC and DC electricity power the world in different ways. AC dominates in large-scale energy distribution, while DC keeps our personal devices running smoothly. Each has its role, shaping the way electricity moves through modern technology. Magnetic field. A magnetic field is an invisible force that influences objects without direct contact. It surrounds magnets, electric currents, and even planets, shaping the way charged particles and materials behave. At its core, a magnetic field is a region of space where a magnetic force is exerted. It's produced by moving electric charges, most commonly seen in magnets and electric currents. The field itself is represented by magnetic field lines which show the direction a magnetic force would push a north pole, if placed within the field. These lines always emerge from a magnet's north pole and loop back toward the south pole, forming closed, continuous paths. To visualize a magnetic field, imagine sprinkling iron filings around a bar magnet. The filings align themselves along the field lines, revealing the otherwise invisible structure of the magnetic field. One of the most significant examples of a magnetic field is Earth's own magnetic field. Generated by molten iron moving in the planet's core, it protects us from harmful solar radiation and guides compasses, helping with navigation. Similarly, the Sun and other celestial bodies have magnetic fields that influence space weather and planetary environments. Magnetic fields also play a crucial role in electromagnetism. When an electric current flows through a wire, it generates a circular magnetic field around it. This principle is used in electromagnets, where coils of wire wrapped around an iron core create a powerful, controllable magnetic field when current passes through. Magnetic fields are essential to countless technologies, from electric motors and transformers to MRI machines and maglev trains. Understanding them allows us to harness their power, shaping everything from modern electronics to large-scale planetary interactions. Magnetic force. Magnetic force is the push or pull that magnetic fields exert on moving charged particles, currents, or other magnets. It's the invisible force behind many everyday phenomena, from the sticking power of refrigerator magnets to the operation of electric motors. At its core, magnetic force arises when charged particles move through a magnetic field. The direction and strength of this force depend on both the velocity of the moving charges and the orientation of the magnetic field. The force is always perpendicular to both the direction of motion and the magnetic field lines, a relationship captured by the right-hand rule. To visualize this, imagine a charged particle moving through space. As it enters a magnetic field, it's deflected sideways, curving along a new path. This deflection explains why charged particles spiral around Earth's magnetic field lines, creating phenomena like the auroras near the poles. Magnetic force also acts between magnets themselves, like poles repel, while opposite poles attract, much like electric charges. This interaction is what keeps magnetic compasses aligned with Earth's field and allows fridge magnets to stick securely to metal surfaces. In technology, magnetic force is fundamental. Electric motors rely on the interaction between current-carrying wires and magnetic fields to produce rotational motion. Generators work in reverse, using motion within a magnetic field to induce electrical current. Magnetic force is everywhere, shaping how we move, generate power, and even navigate the world. Understanding it unlocks the principles behind countless innovations and natural phenomena. Electromagnetic induction. Imagine turning mechanical motion into electricity. This is the power of electromagnetic induction. It's the principle behind generators, transformers, and countless modern technologies that keep the world running. At its core, electromagnetic induction occurs when a changing magnetic field generates an electric current in a conductor. This phenomenon was discovered by Michael Faraday in 1831 when he observed that moving a magnet through a coil of wire produced a current. The key is change. If the magnetic field remains constant, nothing happens. But the moment it fluctuates, an electric current is induced. To visualize this, imagine pushing a loop of wire through a magnetic field. As the wire cuts through the field lines, electrons inside the wire experience a force, causing them to move. This movement is what we call an electric current. This principle is governed by Faraday's law of induction, which states that the induced voltage depends on how quickly the magnetic field changes and how many loops the conductor has. The faster the change, the stronger the induced current. One of the most crucial applications of electromagnetic induction is electric generators. Inside a power plant, turbines spin coils of wire inside strong magnetic fields, continuously generating electricity. The opposite process, using electricity to create motion, is how electric motors work. Another key application is transformers, which use induction to increase or decrease voltage for efficient power transmission. Without them, long-distance electricity distribution would be nearly impossible. Electromagnetic induction is the foundation of electrical power, generation and transmission, shaping everything from how we light our homes to how we charge our devices. It's a principle that converts motion into electricity, unlocking the full potential of electromagnetism. Faraday's law. What if you could generate electricity just by moving a magnet? This is the essence of Faraday's law, a fundamental principle that explains how changing magnetic fields create electric currents. This discovery reshaped science and technology, paving the way for electric generators, transformers, and modern power grids. Faraday's law states that a changing magnetic field induces an electric current in a conductor. In simpler terms, if a wire loop is placed near a moving magnet, the motion of the magnetic field causes electrons in the wire to move, creating a current. The faster the field changes, the stronger the induced current. To understand this, imagine a loop of wire near a bar magnet. If the magnet stays still, nothing happens. But the moment the magnet moves, the magnetic field around it changes, and an electric current flows through the wire. This phenomenon is the foundation of electromagnetic induction. Faraday's law also tells us that the induced voltage depends on how quickly the magnetic field changes and how many loops the conductor has. More loops mean more electrons moving, leading to a stronger current. This principle powers electric generators, where coils of wire spin inside magnetic fields to produce electricity. It also enables transformers, which adjust voltage levels for efficient power transmission. Without Faraday's law, modern electrical power systems wouldn't exist. Every time you charge your phone, use an electric motor, or rely on the grid, you're benefiting from this principle. Faraday's insight revealed a direct link between magnetism and electricity, one that continues to power the world today. Lenz's law. What if every action in electricity triggered an automatic resistance, a force pushing back against change? This is the essence of Lenz's law, a fundamental rule of electromagnetism that governs how induced currents behave. Lenz's law states that when a changing magnetic field induces a current in a conductor, the current flows in a direction that opposes the change that created it. In other words, nature resists change. It doesn't let energy flow freely without pushing back. To see this in action, imagine dropping a strong magnet through a copper tube. Instead of falling freely, the magnet slows down as if moving through an invisible liquid. This happens because the moving magnet induces circular electric currents called eddy currents inside the tube. These currents generate their own magnetic field, which pushes against the magnet's motion, slowing it down. This opposition isn't a coincidence. It's a direct consequence of energy conservation. If the induced current didn't resist the change in the magnetic field, energy could appear out of nowhere, violating fundamental laws of physics. Lenz's law plays a crucial role in real-world applications. Electric brakes and roller coasters use it to slow down carts without friction. Induction cooktops rely on it to generate heat efficiently. Even transformers and electric generators depend on Lenz's law to regulate energy transfer. Understanding Lenz's law reveals how electromagnetism maintains balance. It ensures that every induced current follows a predictable pattern, resisting sudden shifts and stabilizing electrical systems. From industrial machines to everyday appliances, this principle quietly governs the way electricity flows, ensuring that every push meets an equal and opposite resistance. Maxwell's equations. Electromagnetism governs nearly every modern technology, from wireless communication to electric power. At its foundation lie Maxwell's equations, a set of 4 fundamental laws that describe how electric and magnetic fields interact. These equations are the backbone of classical electromagnetism, unifying electricity, magnetism, and light into a single framework. The first equation, Gauss's law, states that electric charges produce electric fields. Imagine placing a charged balloon in space. This equation tells us how the electric field radiates outward, just like gravity extends from a planet. The second, Gauss's law for magnetism, reveals that magnetic fields always form loops. Unlike electric charges, magnetic poles never exist in isolation. Cut a magnet in half and you won't get separate north and south poles. Each half will still have both. Faraday's law of induction is the third equation and explains how changing magnetic fields generate electric fields. This is the principle behind electric generators, where spinning magnets induce current in coils of wire, converting motion into electricity. The final equation, Ampere's law with Maxwell's correction, shows that electric currents create magnetic fields, and that changing electric fields can also generate magnetic fields. This interplay is what allows electromagnetic waves like light and radio signals to propagate through space. Together, Maxwell's equations not only explain everyday electrical phenomena, but also predict the existence of electromagnetic waves, linking light itself to electromagnetism. They transformed physics, paving the way for everything from radio to quantum mechanics. Understanding these 4 equations provides a window into the forces shaping our technological world, making them some of the most profound insights in science. Electromagnetic waves, light, radio signals, and even the warmth of the sun. All of these are carried by electromagnetic waves. Unlike sound, which needs air to travel, electromagnetic waves move through the vacuum of space, carrying energy across vast distances. These waves are not just one thing. They are the result of electric and magnetic fields working together in perfect harmony. An electromagnetic wave is created when an electric charge accelerates, disturbing the surrounding electric and magnetic fields. These disturbances travel outward as waves, with the electric and magnetic components oscillating perpendicular to each other and to the wave's direction of motion. This unique property allows electromagnetic waves to travel without a medium, unlike mechanical waves that require air, water, or solid matter to propagate. The speed of electromagnetic waves in a vacuum is constant, roughly 186,000 miles per second, the speed of light. What differentiates one type of electromagnetic wave from another is its wavelength and frequency. Long wavelength waves like radio waves are used for communication, while shorter wavelength waves like X-rays penetrate materials for medical imaging. In between, visible light represents only a tiny fraction of the electromagnetic spectrum, allowing us to perceive the world through color. Electromagnetic waves are fundamental to modern technology. They enable everything from wireless internet to GPS navigation and medical imaging. The discovery of these waves confirmed that light itself is an electromagnetic phenomenon, linking optics to electromagnetism. Understanding how they behave allows us to harness their properties, shaping everything from everyday communication to cutting-edge physics. Whether seen or unseen, these waves form the invisible backbone of the modern world, carrying information, energy, and even glimpses into the cosmos. Light as a wave. Light is more than just illumination. It's a wave moving through space with precision and speed. But unlike sound or water waves, light doesn't need a medium to travel. It moves through empty space, carrying energy across vast cosmic distances in an instant. At its core, light is an electromagnetic wave, meaning it consists of oscillating electric and magnetic fields that generate each other as they move forward. These fields vibrate perpendicular to each other, forming a self-sustaining wave that propagates through space at an incredible speed. about 300,000 kilometers per second in a vacuum. This wave nature of light explains many of its behaviors. When light passes through a narrow opening, it spreads out. This is diffraction. When it interacts with the surface of a film of oil or a soap bubble, it creates shimmering colors, an effect caused by interference. These phenomena wouldn't be possible if light were simply a stream of particles. The wavelength of light determines its color. Longer wavelengths create red light, while shorter wavelengths shift toward blue and violet. Beyond what our eyes can see, infrared light has even longer wavelengths, while ultraviolet X-rays and gamma rays have much shorter ones. Together, these form the electromagnetic spectrum, a vast range of energy-carrying waves that shape everything from radio signals to medical imaging. Light's wave properties don't just describe how we see the world, they drive modern technologies. Fiber optics, laser precision, and even the colors of a rainbow all stem from light's wave behavior. Understanding light as a wave reveals the hidden structure of reality, showing us that even something as familiar as brightness is a dance of electric and magnetic forces moving through space. Reflection. Look into a mirror and you see yourself staring back, but what you're actually seeing is light bouncing, shifting, and obeying the rules of physics with perfect precision. This is reflection, one of the most fundamental behaviors of light. At its core, reflection happens when light strikes a surface and bounces back. This occurs because light travels in straight lines but changes direction when it encounters a boundary. The way it reflects depends on the surface it hits. A smooth surface like a mirror produces specular reflection, where light rays bounce off in a single organized direction, creating a clear image. This is why you can see your reflection in a calm lake, but not in a rough, choppy ocean. When light hits a rough surface, it scatters in many directions, producing diffuse reflection. This is why most objects don't act like mirrors, but still reflect light enough for us to see them. The law of reflection governs this process. The angle at which light approaches a surface, called the angle of incidence, is equal to the angle at which it bounces away, the angle of reflection. This predictable behavior allows us to design optical instruments from telescopes to laser systems. But reflection goes beyond mirrors. It's why we see the moon, why periscopes let us see around corners, and why polished metals shine. Even colors depend on reflection. A red apple appears red because it reflects red wavelengths while absorbing others. Understanding reflection isn't just about seeing your own image. It's about recognizing how light interacts with the world, revealing details, shaping perception, and defining how we experience everything around us. Refraction. Dip a straw into a glass of water and something strange happens. It appears bent, almost broken. But the straw isn't changing shape. What you're seeing is light being bent as it moves between air and water. This is refraction. Refraction occurs when light passes from one medium to another, changing speed and direction. Light travels fastest in a vacuum, slightly slower in air, and even slower in water or glass. When it moves between these materials, it bends because its speed changes. This bending effect is what makes objects underwater appear distorted or shifted. The amount light bends depends on the refractive index of a material, a measure of how much a substance slows light down. Air has a low refractive index, while water and glass have higher ones. The greater the difference in refractive index, the more light bends. One of the most striking effects of refraction is the illusion of depth in water. A swimming pool always looks shallower than it really is because light rays bend as they exit the water, making objects appear closer to the surface than they actually are. Refraction also plays a critical role in optics. Lenses in glasses, microscopes, and telescopes rely on refraction to focus light and correct vision. It's why rainbows form. Sunlight bends and spreads inside raindrops, breaking into a spectrum of colors. Without refraction, magnifying glasses wouldn't work, eyeglasses couldn't correct vision, and the world wouldn't shimmer through heat waves. It's an invisible force shaping how we see everything, bending light and perception itself. Diffraction. Ever noticed how sound bends around corners? letting you hear someone speaking even when they're out of sight? Or how light spreads when it passes through a tiny gap? This phenomenon is called diffraction, the way waves bend, spread, and interfere when they encounter obstacles. Diffraction happens with all types of waves, including light, sound, and water waves. It occurs when a wave encounters an edge, a slit, or an obstacle and bends around it instead of traveling in a straight line. The smaller the gap compared to the wavelength, the more pronounced the diffraction. You can see diffraction in everyday life. Ever notice the shimmering colors on a CD or the rainbow-like glow from a soap bubble? These patterns arise because light waves diffract off the microscopic grooves, interfering with each other to produce vivid colors. Sound waves, which have much longer wavelengths than light, diffract around doors and walls. This is why you can still hear someone speaking in another room, even if you can't see them. Radio waves, which are even longer, can bend around buildings and mountains, ensuring signals reach areas that would otherwise be blocked. Diffraction plays a crucial role in optics and technology. Scientists use diffraction patterns to study atomic structures in materials, while diffraction gratings are used in spectrometers to analyze light from distant stars. Even in daily life, the ability of waves to bend and spread influences everything from photography to audio design. Though often invisible to the eye, diffraction shapes how waves interact with the world, bending around barriers, creating interference patterns, and revealing the hidden nature of waves in motion. Interference. What happens when two waves meet? Do they collide and cancel each other out? Or do they combine into something new? This is the phenomenon of interference, the way waves interact when they overlap, creating patterns of amplification and cancellation. Interference occurs when two or more waves pass through the same point in space at the same time. When their crests and troughs align, they combine to form a wave with greater intensity. This is called a constructive interference. You can see this effect in the bright bands of light on a soap bubble or the booming sound of two perfectly aligned speakers. But what if the crest of one wave meets the trough of another? They cancel each other out, reducing the wave's intensity, a phenomenon known as destructive interference. Noise-canceling headphones use this principle by detecting external sounds and generating sound waves that interfere destructively, effectively silencing unwanted noise. A striking example of interference is the double-slit experiment. When light passes through two narrow slits, it doesn't simply produce two bright spots on a screen. Instead, it forms a pattern of alternating bright and dark bands. The bright areas occur where waves reinforce each other, while the dark areas mark points of cancellation. This experiment revolutionized physics, proving that light behaves as a wave. Interference isn't limited to light and sound. It governs the behavior of water waves, radio signals, and even quantum particles. From the shimmering colors of a film of oil to the echoes in a concert hall, interference is a fundamental property of waves, revealing the hidden complexity of their interactions. Field concepts. A force can act on an object even when nothing appears to be touching it. This is the essence of field concepts, a fundamental idea in physics that explains how forces extend through space. Instead of requiring direct contact, fields allow objects to influence each other across a distance. A field is a region of space where a force is exerted on objects with the right properties. For example, a gravitational field surrounds any mass pulling other masses toward it. The Earth's gravitational field keeps the moon in orbit and makes objects fall to the ground. Similarly, an electric field exists around charged particles, attracting or repelling other charges depending on their type. A magnetic field influences moving charges and magnetic materials, guiding the motion of compass needles or electric currents. Fields are visualized using field lines, which map out how a force behaves in space. In a gravitational field, these lines always point toward the mass creating the field. In an electric field, positive charges push lines outward, while negative charges pull them inward. The density of these lines indicates field strength. Closer lines mean stronger forces. Unlike physical objects, fields can exist in empty space. The sun's gravitational field extends billions of kilometers, holding planets in their orbits without any direct contact. In electromagnetism, fields play a crucial role in transmitting forces through space, enabling everything from wireless communication to the functioning of electric motors. Fields provide a unified way to understand forces at a distance. They explain interactions that shape the universe, from planetary motion to subatomic forces. By defining how forces extend through space, field concepts form the foundation of classical physics and modern scientific theories. Blackbody radiation. Everything around you, from the sun to the screen you're looking at, emits energy in the form of radiation. But how do objects emit and absorb this energy? The answer lies in blackbody radiation, a fundamental concept in physics that explains how objects glow, radiate heat, and interact with electromagnetic waves. A blackbody is an idealized object that absorbs all incoming radiation without reflecting or transmitting any of it. Because it doesn't reflect light, it appears perfectly black at low temperatures. But as it heats up, it emits radiation across a spectrum of wavelengths. Imagine a piece of metal being heated in a forge. It starts dark, then glows red, orange, and eventually white as its temperature increases. This glow is black-body radiation in action. In the late 19th century, physicists struggled to explain the precise way black bodies emitted energy. Classical theories predicted that as wavelength decreased, the emitted energy would approach infinity, a contradiction known as the ultraviolet catastrophe. The breakthrough came from Max Planck, who proposed that energy isn't emitted continuously, but in discrete packets called quanta. This idea led to Planck's law, which accurately describes blackbody radiation and marked the birth of quantum mechanics. Blackbody radiation is everywhere. The cosmic microwave background, the afterglow of the Big Bang, is the universe's own blackbody signature. Infrared cameras detect thermal radiation based on these principles. Even the colors of stars are dictated by blackbody radiation, with hotter stars appearing blue and cooler ones red. Understanding blackbody radiation was a turning point in physics, bridging classical and quantum theories. It explains why everything with temperature radiates energy and provides the foundation for modern quantum mechanics, astrophysics, and thermal imaging technology. Atomic structure. Everything around you, every solid object, every breath of air, every drop of water, is made of atoms, the fundamental building blocks of matter. Though impossibly small, atoms form the structure of everything in the universe, from the tiniest grain of sand to the most massive stars. At the heart of an atom lies the nucleus, a dense core containing protons and neutrons. Protons carry a positive charge, while neutrons have no charge at all. Surrounding the nucleus is a cloud of electrons, negatively charged particles that move in specific energy levels or orbitals. The balance between positively charged protons and negatively charged electrons holds the atom together through electromagnetic forces. Not all atoms are the same. The number of protons in an atom's nucleus, known as its atomic number, determines which element it is. Hydrogen has just one proton, while carbon has 6 and uranium has 92. But atoms of the same element can still vary. They may have different numbers of neutrons, forming isotopes, which can change an element's stability and properties. The behavior of atoms is dictated by their electrons. Electrons don't move randomly. They exist in defined energy levels. The way these electrons interact and bond with others determines chemical reactions, the forces that shape everything from the air we breathe to the food we eat. Our understanding of atomic structure has evolved from Dalton's solid spheres to Bohr's planetary model and eventually to quantum mechanics, where electrons behave as both particles and waves. This discovery revolutionized fields like chemistry, electronics, and nuclear energy. Atoms are small, yet they hold the secrets to the structure, behavior, and interactions of all matter. A microscopic world that governs everything we see. Photon concept. Light seems continuous, like a smooth beam flowing through space. But at its most fundamental level, light is made of discrete packets of energy, photons. The photon is the smallest unit of light, an indivisible quantum of electromagnetic radiation. Unlike particles of matter, photons have no mass, yet they carry energy and momentum, making them one of the most fascinating building blocks of the universe. The concept of photons emerged from a fundamental problem in physics. Classical wave theories of light failed to explain certain behaviors, like the photoelectric effect, where light striking a metal surface ejects electrons. Albert Einstein proposed a groundbreaking solution. Light isn't just a wave, it also behaves as a particle. He suggested that light is made of quantized packets of energy called photons, with each photon's energy directly proportional to its frequency. This idea revolutionized physics and laid the foundation for quantum mechanics. Photons exhibit properties of both waves and particles, a concept known as wave-particle duality. They travel as waves, interfering and diffracting like ripples on water, yet they interact with matter as discrete particles, transferring energy in precise amounts. This duality allows photons to power everything from solar panels to lasers. Unlike ordinary particles, photons always move at the speed of light in a vacuum. They have no rest mass and experience no passage of time. They enable vision, communication, and even fundamental interactions in particle physics. From the light of distant stars to the signals in fiber optics, photons shape the way we perceive and interact with the universe. Understanding them isn't just about explaining light. It's about unlocking the very nature of reality itself. Photoelectric effect. Light isn't just a wave, it can behave as a particle. This revolutionary idea was confirmed by the photoelectric effect, a phenomenon that reshaped our understanding of physics and helped lay the foundation for quantum mechanics. The photoelectric effect occurs when light strikes a metal surface and ejects electrons from it. At first, this might seem straightforward. If light is a wave, increasing its intensity should provide more energy to the electrons, causing them to be ejected with greater speed. But experiments showed something strange. Increasing the intensity of light didn't always work. Instead, electrons were only ejected if the light had a high enough frequency, no matter how bright the light was. This contradiction puzzled scientists until Albert Einstein proposed a radical solution in 1905. He suggested that light isn't just a wave, but is also made of particles called photons, each carrying a discrete packet of energy. The energy of a photon is determined by its frequency, not its intensity. If a photon has enough energy, it can knock an electron free from the metal. If it doesn't, no electrons are ejected, no matter how many photons hit the surface. Einstein's explanation was groundbreaking. It proved that energy is quantized and that light has particle-like properties, reinforcing the idea of wave-particle duality in quantum mechanics. This discovery not only won Einstein the Nobel Prize in Physics, but also led to the development of photoelectric cells, which are used in everything from solar panels to digital cameras. The photoelectric effect shattered classical physics, proving that light behaves in ways once thought impossible. It demonstrated that reality at the smallest scales doesn't follow everyday intuition. It follows quantum rules, where energy moves in packets, and light is both a wave and a particle. Dimensional analysis. Picture trying to check if a bridge will hold under pressure, or if an equation describing motion actually makes sense. In physics, one tool ensures consistency across calculations. Dimensional analysis. It's a method that helps verify equations, convert units, and even derive new physical relationships by examining the fundamental dimensions of physical quantities. Suit work. Every physical quantity can be broken down into basic dimensions: mass, length, time, temperature, electric current, amount of substance, and luminous intensity. These dimensions form the foundation of all physical equations. For example, velocity has dimensions of length per unit time, while force is expressed as mass times acceleration. Dimensional analysis ensures that equations remain consistent. If the left and right sides of an equation don't match in terms of fundamental dimensions, the equation is incorrect. This is why speed can't be added to energy, because their dimensions are fundamentally different. This method also helps in unit conversions. If a car travels at 60 kilometers per hour and you need the speed in meters per second, Dimensional analysis ensures that multiplying by the right conversion factors maintains consistency. Another powerful use is in deriving relationships. Even if an exact equation is unknown, dimensional analysis can suggest possible forms of equations. For instance, analyzing the period of a simple pendulum leads to the conclusion that it depends on the square root of the length divided by gravitational acceleration, just by examining dimensions. Dimensional analysis acts as a safeguard against mathematical errors and provides insights into how physical quantities relate. Whether checking an equation, converting units, or uncovering patterns, it remains an essential tool in physics, ensuring calculations align with the fundamental principles governing reality. Scaling laws. Scaling laws govern how physical properties change when an object's size is altered. Whether in engineering, biology, or physics, these principles determine how structures hold together, how animals function, and how forces interact across different scales. They reveal why a tiny insect can survive a fall from a great height, while a larger animal cannot, and why structures must be designed differently depending on their size. At the core of scaling laws is geometric similarity. When an object is scaled up or down, its length, area, and volume don't increase at the same rate. If the length of an object doubles, its surface area increases by a factor of 4, while its volume grows by a factor of 8. This explains why larger animals need proportionally thicker bones to support their weight. Mass increases faster than the strength of their bones. In fluid dynamics, similarity principles help predict how different size systems behave under similar conditions. The Reynolds number, for example, determines whether fluid flow is smooth or turbulent, regardless of whether it's in a laboratory experiment or a full-scale airplane. Engineers use this principle to test scale models before building actual structures, ensuring accurate predictions. Scaling laws extend beyond mechanics. In thermal physics, heat dissipation depends on surface area, which is why smaller objects cool down faster than larger ones. In electromagnetism, circuits behave differently depending on their scale, influencing everything from microchips to power grids. By understanding scaling laws and similarity, scientists and engineers can predict how structures, organisms, and systems behave when size changes. These principles shape the natural world and the technology around us, ensuring that designs, whether biological or man-made, function efficiently across different scales. Nonlinear dynamics. Not all systems behave in predictable, straightforward ways. Some evolve in ways that are highly sensitive to initial conditions, where small changes lead to drastically different outcomes. This is the world of nonlinear dynamics, where systems defy simple proportionality and exhibit complex, often chaotic behavior. In linear systems, outputs scale directly with inputs. Double the force and an object moves twice as fast. But in nonlinear systems, relationships are not so simple. A small push might result in a minor change, or it might set off a chain reaction. Weather patterns, fluid turbulence, and even population growth are governed by nonlinear dynamics. One of the defining features of nonlinear systems is sensitivity to initial conditions. This is famously demonstrated in the butterfly effect, where a tiny disturbance, like a butterfly flapping its wings, can alter weather patterns halfway across the world. This unpredictability is a hallmark of chaotic systems, which, while deterministic, are practically impossible to forecast over long periods. Another feature of nonlinear dynamics is self-organization. In systems like chemical reactions or traffic flow, patterns emerge spontaneously despite the lack of a central governing force. Feedback loops play a crucial role, where effects can reinforce or suppress changes in unexpected ways. Nonlinear dynamics appear everywhere, from electrical circuits to planetary motion. In engineering, understanding these systems helps design stable bridges and aircraft. In medicine, it explains irregular heartbeats and neural activity. While these systems may appear random, underlying patterns often exist, revealing deep insights into how nature and technology operate beyond simple cause and effect. By studying nonlinear dynamics, physicists uncover the underlying order within seemingly chaotic behavior. allowing for better predictions and control in systems that once seemed unpredictable. Chaos theory. Small causes can lead to massive, unpredictable effects. This is the essence of chaos theory, a branch of mathematics and physics that studies how complex systems evolve in ways that appear random yet follow underlying patterns. Even in deterministic systems, where outcomes are governed by clear rules, chaos emerges when tiny differences in starting conditions amplify over time. One of the most well-known ideas in chaos theory is the butterfly effect, the concept that a minor disturbance, like a butterfly flapping its wings, could alter weather patterns across the globe. This illustrates sensitivity to niche conditions, where even the smallest change in input can produce vastly different outcomes. Chaotic systems are not truly random. They operate within well-defined boundaries called attractors. One example is the Lorentz attractor, discovered by meteorologist Edward Lorenz. When studying weather models, he found that rounding the decimal in his data by an amount seemingly too small to matter led to entirely different weather predictions. This demonstrated that long-term forecasts for chaotic systems are inherently limited. Chaos appears in a wide range of natural and technological systems. It governs fluid turbulence, electrical circuits, planetary motion, and even population dynamics. In medicine, chaotic patterns emerge in heart rhythms, neural activity, and disease spread. Engineers and scientists use chaos theory to predict, manage, or even harness chaotic behavior in practical applications. Unlike simple cause and effect relationships, chaos theory reveals that many systems follow unpredictable yet structured patterns. While the future of a chaotic system can never be precisely determined, understanding its behavior allows for better modeling and control. Chaos is not disorder. It is a deeper form of complexity, where apparent randomness masks an intricate underlying order. Special relativity. Nothing in the universe moves faster than light. This simple fact, uncovered by Albert Einstein in his theory of special relativity, reshaped our understanding of time, space, and motion. Unlike the fixed, absolute space and time of classical physics, Einstein revealed that these are not rigid and unchanging. They are flexible, interconnected, and relative. The key idea behind special relativity is that the laws of physics are the same for all observers in uniform motion, and that the speed of light is constant, regardless of the observer's motion. This has profound consequences. Time and space are not absolute, but depend on the relative motion of observers. For instance, time dilation means that a moving clock ticks more slowly compared to one at rest. If you were traveling near the speed of light, you'd age more slowly than people who stayed behind. Length contraction means that objects moving at high speeds appear shorter along the direction of motion. These effects are not just theoretical. They've been confirmed through experiments. Particle accelerators observe time dilation in short-lived particles moving near light speed. GPS satellites account for time dilation to maintain precise positioning. Special relativity also redefined energy and mass with the famous equation EmC2, showing that mass and energy are interchangeable. A small amount of mass can be converted into a tremendous amount of energy, a principle behind nuclear power and atomic weapons. Einstein's theory replaced the Newtonian notion of absolute time and space with a new framework, where measurements depend on the observer's state of motion. It revealed that space and time are woven together in a four-dimensional fabric called space-time, forever changing our understanding of the universe. Special relativity. Special relativity is the idea that the laws of physics are the same for all observers in uniform motion, no matter how fast they're moving. If you're traveling in a spaceship at constant speed, the same physical rules apply to you as they do to someone standing still on Earth. But here's the twist. If you observe someone moving at high speed relative to you, strange things start happening. One of the most famous effects is time dilation. When an object moves close to the speed of light, time for that object slows down relative to a stationary observer. If astronauts were to travel at near light speed and return to Earth, they would have aged far less than those who stayed behind. Another effect is a length contraction. where objects moving at extreme speeds appear shorter along their direction of motion. Einstein's equations also revealed mass-energy equivalence, expressed in famous equation EMC2. This showed that energy and mass are interchangeable, explaining why nuclear reactions release enormous amounts of energy. Special relativity isn't just theoretical. It underpins technologies like GPS satellites, which must account for time dilation to provide accurate location data. It also set the stage for general relativity, where Einstein extended these ideas to explain gravity's effect on space and time. By reimagining motion, special relativity shattered old assumptions and revealed a universe where time, space, and energy are deeply connected. Mass-energy equivalence. Mass and energy are not separate entities. They are interchangeable. This principle, known as mass-energy equivalence, reveals that mass can transform into energy and vice versa, fundamentally reshaping our understanding of the universe. Einstein's equation. EMC2 states that even a tiny amount of mass can convert into an enormous amount of energy. This is because the speed of light c is a vast number, and when squared, it magnifies the energy output dramatically. This principle explains why nuclear reactions, where small amounts of matter transform into energy, can power stars or unleash the force of atomic bombs. In everyday life, mass-energy conversion is not noticeable because most objects don't undergo such transformations. However, it constantly operates at the atomic level. In the Sun, nuclear fusion fuses hydrogen into helium, releasing the energy that fuels our planet. Particle accelerators smash subatomic particles together, briefly converting energy into new particles with mass, demonstrating that energy itself can manifest as mass under the right conditions. Mass-energy equivalence also plays a role in modern technology. PET scans in medicine rely on the annihilation of tiny particles, converting mass into detectable energy. Even nuclear power plants generate electricity by applying this principle to controlled reactions. This discovery reshaped physics, linking matter and energy in a way once thought impossible. It laid the foundation for nuclear science, quantum mechanics, and modern cosmology, proving that at its most fundamental level, the universe is a continuous interplay of mass and energy, seamlessly transforming in ways that govern the cosmos. General relativity. Gravity isn't just a force, it's the bending of space and time itself. This is the foundation of general relativity, Albert Einstein's groundbreaking theory that redefined our understanding of gravity. Unlike Newton's classical view, where gravity is a force pulling objects together, Einstein showed that gravity emerges from the curvature of space-time caused by massive objects. Imagine placing a heavy ball on a stretched rubber sheet. The sheet bends, creating a depression. Now, if you roll a smaller ball across the surface, it won't move in a straight line. It will curve around the larger ball just like planets orbit the sun. This bending of space-time explains why objects follow curved paths under gravity's influence. One of general relativity's key predictions is gravitational time dilation, the idea that time moves slower in stronger gravitational fields. Clocks on Earth's surface tick slightly slower than those on a satellite in orbit. This effect is real and measurable, and it's essential for GPS satellites to function accurately. Another consequence is gravitational waves, ripples in space-time produced by massive, accelerating objects like merging black holes. These waves were first detected in 2015, confirming yet another prediction of Einstein's theory. Perhaps the most extreme prediction of general relativity is the black hole, a region where gravity is so strong that nothing, not even light, can escape. The existence of black holes, once theoretical, is now confirmed through astronomical observations. Einstein's theory transformed physics, explaining everything from planetary motion to the structure of the universe itself. It remains one of the most successful theories in science, continually tested and confirmed through experiments and observations, proving that space and time are not fixed, but dynamic, shaped by the presence of mass and energy. Quantization. In everyday life, we think of things as continuous. You can pour water smoothly into a glass, increase the volume of music gradually, or move at any speed you like. But at the smallest scales of reality, nature doesn't work that way. It operates in discrete steps, a fundamental concept known as quantization. Quantization means that certain physical properties like energy, charge, and angular momentum can only exist in specific indivisible amounts. This idea revolutionized physics, challenging the classical assumption that everything varies smoothly. Instead, many properties behave like a staircase rather than a ramp. Only certain steps are allowed, with no in-between values. A prime example is energy levels in atoms. Electrons don't orbit a nucleus at just any distance. They exist in specific energy levels, like rungs on a ladder. When an electron jumps between these levels, it must absorb or emit an exact amount of energy. This is why atoms produce distinct spectral lines rather than a continuous rainbow. Quantization is also evident in electric charge. The charge of a single electron is a unit, meaning all charges in the universe are integer multiples of this fundamental value. There is no such thing as half an electron's charge. Perhaps the most famous quantization principle comes from Max Planck's discovery that energy itself is quantized at the microscopic level. Light, once thought to be purely a wave, was found to be made of discrete packets called photons, each carrying a fixed amount of energy depending on its frequency. Quantization is what makes quantum mechanics distinct from classical physics. It governs the behavior of atoms, semiconductors, and even the fundamental forces of nature, defining the very limits of how energy and matter interact. Wave-particle duality. Light moves like a wave, spreading out and interfering with itself. But shine that same light on a metal surface and it behaves like a stream of particles, knocking electrons free. This paradox sits at the heart of wave-particle duality, one of the most fundamental mysteries of quantum mechanics. For centuries, physicists debated the true nature of light. In the 17th century, Isaac Newton described light as a stream of tiny particles, while Christian Huygens argued that it behaved as a wave. The debate seemed settled in the 19th century when Thomas Young's famous double-slit experiment demonstrated that light creates an interference pattern, a hallmark of waves. But then came the photoelectric effect, where shining light on a metal surface ejected electrons. Albert Einstein explained this using quantized packets of light, photons, showing that light also behaved like a particle. This discovery earned him the Nobel Prize and shattered the classical understanding of physics. The mystery deepened with quantum experiments on electrons, and even large molecules, showing they too exhibit wave-particle duality. When unobserved, they interfere like waves, but the moment they are measured, they behave like particles, as if observation itself forces them to choose a nature. This duality isn't just a quirk of light and electrons. It applies to all quantum particles, forming the foundation of quantum mechanics. It explains phenomena like electron orbitals, where electrons don't move in fixed paths, but exist as probability waves. Wave-particle duality challenges our classical intuition, revealing that reality isn't as straightforward as it seems. The same entity can exhibit two seemingly contradictory behaviors depending on how we observe it. It's a principle that reshaped physics, leading to modern quantum theory and groundbreaking technologies. Uncertainty. Principle. You cannot know exactly where particle is and how fast it's moving at the same time. This isn't a limitation of our instruments. It's a fundamental property of reality itself. This is Heisenberg's uncertainty principle, one of the core ideas of quantum mechanics. Proposed by Werner Heisenberg. In 1927, the uncertainty principle states that the more precisely we measure a particle's position, the less precisely we can know its momentum, which is its mass times velocity. Conversely, if we pin down its momentum, its position becomes uncertain. This isn't just a matter of experimental difficulty, but a built-in feature of the quantum world. A useful analogy is trying to take a sharp photo of a moving object. If the shutter speed is slow, the object is blurred, making it hard to tell exactly where it is. If the shutter speed is fast, you get a clear position but lose information about how fast it was moving. In the quantum world, this blur isn't due to technological limitations. It's an intrinsic part of nature. At the heart of this uncertainty is wave-particle duality. Particles at the quantum scale, like electrons, behave as both waves and particles. The more we try to confine an electron's position, the more its wave-like nature forces its momentum to spread out unpredictably. This principle has profound implications. It defines quantum mechanics, shaping how electrons behave in atoms, and why particles never have precise classical paths. It's also why quantum systems must be described using probabilities rather than exact values. The uncertainty principle isn't a flaw in physics. It's the reason the quantum world works the way it does, governing everything from semiconductor technology to the structure of atoms themselves. Quantum mechanics. At the smallest scales of reality, the rules of physics change. Particles no longer behave like tiny, predictable objects, but instead exist in strange, probabilistic states. This is the foundation of quantum mechanics, the branch of physics that governs the behavior of matter and energy at the atomic and subatomic levels. One of its most famous principles is wave-particle duality. Light, once thought to be purely a wave, can also behave like discrete particles called photons. Similarly, electrons, normally considered particles, can spread out like waves and interfere with themselves, as demonstrated in the double-slit experiment. When electrons are fired at two slits, they don't just pass through one or the other. They create an interference pattern, behaving like waves until they are observed. The mere act of measurement forces them into a definite state. This ties into another key concept: superposition. Unlike classical objects, quantum particles don't have fixed properties until they are measured. An electron, for example, can exist in multiple energy states at once, only collapsing into one when observed. This idea extends to quantum computing, where qubits can exist in multiple states simultaneously, vastly increasing computational power. Then there's quantum entanglement, where two particles become linked no matter how far apart they are. A change in one instantaneously affects the other, seemingly violating classical notions of space and time. Einstein famously called this spooky action at a distance. Quantum mechanics underpins modern technology, from lasers and semiconductors to quantum encryption. Yet it remains full of unanswered questions, challenging our understanding of reality itself. It's a world where certainty gives way to probability, where particles defy classical intuition, and where the fundamental nature of existence is still being explored. Quantum entanglement. Two particles separated by vast distances somehow remain mysteriously connected. Change one, and the other instantly responds no matter how far apart they are. This is quantum entanglement, one of the most baffling and counterintuitive phenomena in physics. At the quantum level, particles don't behave like tiny billiard balls following predictable paths. Instead, they exist in a superposition of states, meaning their properties remain undefined until measured. But when two particles become entangled, their states become linked, no matter how far apart they travel. Measuring one instantly determines the state of the other. Imagine flipping two coins, but instead of landing randomly, they always match, whether heads or tails, even if one is on Earth and the other on the Moon. This defies classical logic. In the early 20th century, Einstein famously called it spooky action at a distance, because it seemed to violate the idea that information cannot travel faster than light. But experiments have confirmed that entanglement is real, and it plays a crucial role in modern quantum mechanics. Entanglement has profound implications. It challenges our understanding of space and time, suggesting that quantum information doesn't behave like ordinary signals. It also forms the foundation of quantum computing, where entangled qubits perform complex calculations far beyond classical computers. In quantum cryptography, entanglement ensures ultra-secure communication, as any attempt to eavesdrop disrupts the system. While physicists still debate the full implications, entanglement remains one of the most striking demonstrations of the quantum world's unpredictability. It's a phenomenon that defies intuition, yet drives cutting-edge advancements in science and technology, pushing the boundaries of what we know about the universe. Quantum decoherence. Quantum decoherence explains why the strange rules of quantum mechanics don't seem to apply in our everyday world. At the quantum level, particles exist in a superposition, meaning they can be in multiple states at once. But in the macroscopic world, objects have definite positions and behaviors. What happens in between? That's where decoherence comes in. In quantum mechanics, particles are described by wave functions, mathematical expressions that encode all possible states of a system. As long as a system remains isolated from its environment, these wave functions maintain their delicate superpositions. But the real world isn't isolated. Every particle constantly interacts with its surroundings. The moment a quantum system interacts with its environment, whether through air molecules, radiation, or even the measuring process, it loses its coherence. The wave function collapses, and instead of existing in multiple states, the system settles into a single definite outcome. Think of it like ripples on a still pond. If no disturbances occur, the ripples maintain a smooth, predictable pattern. But if you throw in a handful of pebbles, the water becomes chaotic, and the ripples lose their distinct shapes. Decoherence works similarly. It's the interference caused by interactions that disrupt a quantum system's ability to remain in superposition. This process doesn't mean quantum mechanics stops working. Instead, it explains why classical reality emerges from a quantum world. Without decoherence, the everyday world would behave like Schrödinger's cat. Objects wouldn't have fixed states until observed. Decoherence is a major challenge in quantum computing. Quantum bits, or qubits, rely on superposition to perform complex calculations, but environmental interference can cause decoherence, erasing information. Understanding and controlling decoherence is crucial to advancing quantum technology and unlocking the full potential of quantum mechanics. Renormalization. Renormalization is a powerful mathematical technique that helps make sense of infinite quantities in quantum field theory. Without it, many equations in physics would break down, giving nonsensical results instead of meaningful predictions. At the quantum level, particles don't just interact directly. They constantly emit and absorb virtual particles, creating a sea of fluctuations. These interactions, when calculated naively, lead to infinite values. For example, the charge of an electron or the mass of a particle might seem to blow up to infinity, making the equations meaningless. Renormalization solves this by introducing a systematic way to handle infinities. Instead of treating these infinities as physical, physicists redefine the fundamental parameters like mass and charge so that only the measurable, finite quantities remain. It's like adjusting the zoom on a camera. At different scales, details change, but the overall picture remains consistent. One of the most famous applications of renormalization is in quantum electrodynamics, QED, the theory describing how light and charged particles interact. Initially, the equations of QED predicted infinite results for observable properties, but renormalization corrected these infinities, producing calculations that matched experiments with astonishing precision. Beyond QED, renormalization plays a role in quantum chromodynamics, QCD, the theory of strong nuclear forces, and even in condensed matter physics, helping explain phase transitions in materials. The idea extends to understanding how physical laws change at different energy scales, revealing deeper connections between forces in nature. Quantum field. Theory. Everything around you, from the screen you're looking at to the air you breathe, is made of particles. But what if particles aren't the fundamental building blocks of reality? Quantum field. Theory, QFT, reveals that what we call particles are just excitations in invisible fields that stretch across the universe. In classical physics, particles are seen as tiny solid objects moving through space. But in QFT, the universe is described as a collection of quantum fields, one for each fundamental force and type of particle. These fields are like an ocean, and particles are the ripples that emerge when energy disturbs the surface. For instance, an electron isn't a tiny isolated object, it's a localized disturbance in the electron field. QFT combines the principles of quantum mechanics and special relativity, explaining how particles appear, interact, and vanish. One of its major successes is describing the electromagnetic field through quantum electrodynamics, QED, which explains how light and charged particles interact. This framework is incredibly precise. Its predictions match experiments to an accuracy of 1 part in a billion. QFT also underlies the standard model of particle physics, unifying 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It predicts the existence of particles like the Higgs boson, which was experimentally confirmed in 2012, proving how particles acquire mass. At its core, quantum field theory reshapes how we understand existence, not as a collection of tiny objects, but as a universe woven from fundamental fields. Though it's one of the most successful theories in physics, it remains incomplete, leaving questions about gravity, dark matter, and the nature of space-time itself still unanswered.